There is a photograph from Mars that NASA has not officially released, but it can be found online if you know where to look. The photo depicts a faint blue anomaly at precise coordinates in the sky, where the interstellar object designated Tri-I Atlas passed during its closest approach on October 3, 2025. The image was captured by the Mastcam-Z camera of the Perseverance rover, processed by a citizen scientist with the support of Harvard astrophysicist Avi Loeb, and immediately sparked debates among skeptics who see artifacts in the processing where others see confirmation. That's why it matters. All space telescopes tracking this object showed carbon dioxide chemistry and a neutral greenish color. The blue color does not fit into this picture. Blue indicates a possible instrument error, atmospheric effects, or something with reflective properties unrelated to comets. If you add to this 7 other statistical anomalies near the ecliptic trajectory, nickel without iron and morphology directed toward the sun, it results in an object that is difficult to explain in terms of natural causes. An image leak is a crack in the narrative, a moment when information slipped from institutional control and sparked an unresolved conversation. Stay with us until the end, for what this image reveals is not on the surface but in the silence that followed. Before delving into what it all truly means, consider subscribing if you enjoy these nightly explorations and comment where you're watching from today. I would also be interested to know your opinion. Do you think this image is real or part of a wider conspiracy? Let's figure it out. Part 1. A leak that shocked the community. Someone posted an image from Mars and it could rewrite the rules of everything we thought about what moves between the stars. On October 3, 2025, an interstellar object designated Tri-I Atlas approached Mars at a minimum distance. 29 million kilometers separated the red planet from something that should not have been there, something that crossed the void between solar systems to arrive at our cosmic doorstep with such precision that it bordered on suspicion. Space agencies around the world directed their instruments at the flyby window. NASA, ESA, observatories on Earth and in space, all were watching, all waiting for data to tell us what it really was. The public awaited images, spectroscopy, confirmations, but instead received silence, followed by something much more interesting. On the Blue Sky platform, a folded image was published by astrophotographer Simon Schmous. It displayed images from the Mastcam-Z instrument of the Perseverance rover, carefully overlaid to reveal faint signals invisible in single exposures. In the foretold position in the sky for Tri-I Atlas, there it was, smeared, faint, blurred, barely noticeable against the backdrop of the Martian night, but undoubtedly blue. Avi Loeb, an astrophysicist from Harvard who built a career on asking uncomfortable questions about interstellar visits, enhanced the significance of the image with a simple caption, giving it the weight of institutional credibility. The NASA research agency, the Jet Propulsion Laboratory of the California Institute of Technology, Arizona State University, and Simon Schmous. He described it as a faint spot in the predicted location, recorded by overlaying several frames from the Mastcam-Z camera. If this is indeed the case, it will be the first instance where a tool on the surface of Mars has detected an interstellar object in real time during its close approach. This image has stirred the community, already poised for debate. For several weeks, tools operating in space painted a picture of the 3-component object Atlas as something unusual, yet ultimately explainable. It was rich in carbon dioxide and sometimes appeared slightly greenish in processed images, with a coma stretching hundreds of thousands of kilometers into space. Spectroscopy was strange but interpretable. The morphology was unusual but could be modeled. Everything pointed to an exotic comet, formed under conditions not observed in our solar system, ejected from a distant planetary system, and now passing by on a trajectory that will never repeat. But this image from Mars showed a blue color, not green or neutral. This single chromatic discrepancy opened a rift in the online community of astronomers, which will only widen in the coming days. Loeb's formulations carried weight because he built arguments. His reports on the 3-component object Atlas accumulated evidence over several weeks, stacking anomaly upon anomaly, each explainable but collectively causing concern. The sun shone in a way uncommon for ordinary comets. Spectroscopic signatures indicated ratios of industrial metals, and polarization measurements exceeded known comet families, revealing a blue spot from the surface of Mars, leaked through unofficial channels while official data remained locked behind verification processes in the agency. Their origin mattered. This was not a NASA press release. It was not peer-reviewed data published in scientific journals. It was a dataset from a citizen scientist shared on social media, supported by a controversial but competent astrophysicist, and immediately used by both supporters and skeptics. What could it mean if the image turned out to be authentic? It seems that the surface brightness must have been high enough for a non-astronomical tool designed for daytime geology to capture it in several exposures. This implied either favorable observation geometry, an unusually reflective surface, or something that emits or scatters light much more efficiently than typical dusty comets. The conservative interpretation suggested that we see scattered sunlight from the same carbon coma already characterized by JWST and Sphere X. The geometry was correct. Mars was in a favorable line of sight during the flyby. A multitude of overlaid frames could indeed highlight a weak source from the noise, but the speculative interpretation was much more provocative. What if the signal came not from diffuse gas and dust, but from a structured, reflective surface? What if the Triad Atlas is not a comet at all, but something created to look like a comet from afar, revealing its true nature only upon close approach? The division among the audience happened instantly and sharply. The believers saw confirmation of what Loeb had been saying all along. It was irrefutable evidence, the first mass confirmation of the presence of an interstellar object that could be unnatural. The overlaid frames showed exactly what the models predicted: a weak but detectable signal in the right coordinates of the sky, visible only through careful processing. Skeptics raised legitimate questions about the processing methodology. How were the frames aligned? What color weight value was applied during the overlay? Were there cosmic ray hits or hot pixels in this place that could be masked as a real signal? Without access to the original footage, independent verification was impossible, and this impossibility became fuel for the narrative. The inappropriate color confused everyone who noticed it. Space instruments with finely calibrated spectroscopy showed that carbon dioxide dominates the coma, while water vapor is a secondary component with traces of neutral atoms of nickel and iron. Carbon dioxide in comas usually does not appear blue. It scatters sunlight with a neutral or slightly greenish hue depending on the properties of the grain and the geometry of observation. The blue color implies something else: Rayleigh scattering from very fine particles, possibly, or mirror reflection from a smooth metallic surface. Either this is just an artifact of processing through the Z-array. The blue blur raised more questions than answers, and that was what mattered. In the gap between what we expected to see and what appeared in this leak, a whole universe of speculation quickly filled the void. We need to understand what happened here, not just the image itself, but also the mechanics of how it leaked, why Array Z was a strange choice for such observation, and what the color tells us about the object or tool. Then we need to ask a more complex question. If this discovery is real, what does it imply about the nature of the triad of the Atlas? And if it is not real, why has it resonated so strongly with an audience already attuned to the idea that something unusual is hidden in plain sight? Part 2. The anatomy of the alleged leak. The image did not go through official channels, and this matters more than you might think. Simon Schmalz published his overlay frames of the Z-array on the Blue Sky platform on October 4, 2025, about 24 hours after the Triad Atlas approached Mars at minimum distance. The publication contained technical details regarding frame selection, alignment methodology, and coordinate prediction that he used to determine where an object should appear in the Martian sky. Lowe quickly grasped this information, incorporating it into a central article that framed the discovery within his broader narrative about the anomalies of the three-eyed Atlas. The indication of the source gave the material institutional legitimacy, despite bypassing all standard checks typically imposed by the Perseverance mission on data publication. It was a manifestation of citizen science in its most powerful and problematic form. Powerful because it demonstrated that curious people with the necessary skills can extract signals from public data that agencies have not yet flagged. Problematic because without independent verification from other analysts working with the same raw footage, we had no way to distinguish the real signal from processing artifacts. The stacking method used in astrophotography is applied to extract faint objects from noise by combining multiple exposures. The principle is simple. Random noise is averaged over the frames while the true signal accumulates. If you align 10 images of the same field and stack them, the noise decreases by the square root of 10, while the signal increases linearly. However, as always, the main problem is alignment. Small registration errors between frames can create chromatic artifacts, especially if the object moves relative to the starry background. Incorrect alignment of color channels during stacking can lead to unexpected glows unrelated to the target's physical spectrum. Atmospheric dispersion, even in the thin atmosphere of Mars, can separate colors differently at low altitudes. And if the object is so weak that it barely exceeds the detection threshold in individual frames, then perceptual bias becomes a real problem. We see what we expect to see, especially when searching for something we desperately want to find. The Mars CAMSI camera was never meant for such work. This is a zoomable multispectral stereo camera mounted on the Perseverance mast, optimized for geological studies, panoramic landscape shots, and detailed rock texture analysis. The instrument has 11 narrowband filters covering the visible and near-infrared ranges, allowing it to characterize the mineralogical composition and atmospheric properties on a Martian day. It can enlarge images from 34 millimeters to 110 millimeters equivalent focal length, giving it versatility for both wide fields and detailed objects. However, at its core, this is a daytime geology camera, not a tool for deep space astronomy. It lacks the long exposure capability, tracking precision, and low noise levels characteristic of specialized astronomical instruments. Its usual application is related to illuminated sunny bottoms of craters and dunes where wind traces are visible, rather than weak interstellar point sources passing through the night sky. The field of view and pixel scale create additional challenges. Even at maximum zoom, the mast CAMSI camera covers a relatively wide area of the sky compared to the telescope. Weak light sources outside the axis can create internal reflections and ghostly images that appear in predictable places based on optical design. The noise of the sensor, especially during long night exposures, leads to the appearance of hot pixels and cosmic ray bursts that must be carefully filtered during processing. The atmosphere of Mars, although thin, still scatters sunlight even at night, especially near the horizon. Dust suspended in the Martian air faintly glows in the scattered twilight and starlight, creating a variable background that shifts with atmospheric density and observation height, complicating the detection of faint objects. A faint spot may be real, or the result of the interaction of several instrumental and ecological effects that coincidentally aligned at the predicted coordinates for the Tri-1 Atlas. The question of raw data became central to the discussion a few hours after the leaked dataset appeared. If Shamaus really discovered the 3-to-1 Atlas in the mast CAMSI camera footage, then, in principle, any other analyst with access to the same raw data could reproduce this result. NASA makes raw images from the Perseverance rover publicly available through the mission's online archive, usually within a few days of being received. However, reproducibility requires precise knowledge of which frames were used, their timestamps, the rover's direction, and the calibration steps applied before overlaying. Without this metadata, independent verification becomes a true ghost hunt. You can view dozens of night shots from the corresponding observation window and still not find the exact combination that would give the original set. If you find potential frames but cannot reproduce the spot, does that mean the detection was false, or did you simply use a different processing method? There were alternative ways to confirm this that were publicly discussed in the days following the closest approach. Mars orbiters, especially the HiRISE camera on the Mars Reconnaissance Orbiter, Mars Express, and the ExoMars Trace Gas Orbiter, had potentially more advantageous geometry for detecting the 3-1 Atlas during the flyby window. Loeb himself noted HiRISE as a critically important asset in his essays before the flyby, stating that its high resolution can limit the object's diameter by measuring whether any individual pixel shows abnormal brightness. The spatial resolution of HiRISE is about 30 kilometers per pixel at a distance of 3-to-1 from Atlas, meaning that a sufficiently bright compact source could saturate individual pixels or create a detectable scattering function, even if the object was much smaller than the pixel scale. But the HiRISE data, like the mast cam data, undergoes internal verification before publication, and the interval between receipt and publication can stretch from days to weeks, depending on mission priorities and the complexity of analysis. Numerous and well-founded explanations for the appearing spot deserve serious attention. Hot pixels often occur in CMOS sensors, especially during long exposures or in variable temperature conditions. A malfunctioning photopixel in the expected place could create the faint stationary signal visible in the stacked frames. Cosmic rays constantly hit detectors, creating bright but brief events that, if they accidentally strike the same pixel location in several frames, can appear as a real astronomical source. Dust particles on the protective window of the instrument or internal optical elements can scatter light in complex ways, creating faint halos or side glows. Compression artifacts in JPEG or PNG files used for public distribution can create bands, color changes, or false details that were not present in the raw uncompressed frames. Registration errors during the overlay process, especially if the frames were taken from slightly different angles or focal lengths, can create edge effects and chromatic distortions. And finally, there is always the possibility that an unsuitable background star, located near the predicted path of the object Trian Atlas, creates a real astronomical signal unrelated to the interstellar object. The blue color remained the most provocative and at the same time the most suspicious element. Assumptions about white balance play a huge role in RGB images. Raw footage from Mascamzi captures light in 11 separate spectral ranges that need to be combined and color balanced to create a visually intuitive RGB image easily perceived by humans. Different assumptions about lighting conditions, atmospheric transparency, and object properties can significantly alter the color balance. Process data stream optimized for Martian daylight, where the light spectrum reddens due to atmospheric scattering, can activate color channels in a way that leads to artifacts when applied to faint targets in the night sky. Small differences in how the array of biofilters is demosaicked during transformation can cause color changes, especially at low signal-to-noise ratios. Atmospheric effects even on Mars can selectively scatter shorter wavelengths depending on dust load and viewing geometry. A truly colorless or neutral source may appear blue if the processing suggested a redder background than actually existed. But there is a more intriguing possibility that requires a cautious approach, as it involves speculation. If Tri and Atlas have a reflective metallic surface rather than a diffuse, dusty comet, certain assumptions about white balance in image processing may shift the color towards blue under the Martian night sky. Metals like aluminum or stainless steel have relatively flat reflection spectra in the visible range, meaning they reflect sunlight without significant color bias. However, if the processing system expected a warm light source, as is typical in daytime shooting on Mars, and then encountered a relatively neutral reflector illuminated by sunlight that did not pass through filters and reflected off the surface or atmosphere of Mars, color correction could lead to distortion, emphasizing a blue tint. This assumption is less likely than simple processing artifacts, but it demonstrates how much we need original footage and transparent methods to distinguish physical reality from instrumental effects. Color mismatch is a signal that requires reproducibility. We cannot draw conclusions about physics based on color images processed through unknown systems and spread on social media. We need the original frames. Independent analysts are required to apply various processing methods and compare results. Spectroscopic data from Martian instruments is also needed, if such capabilities exist, or at least multiband photometry that could show whether the blue hue is real or artificial. Until we have these confirmations, the unclear spot remains exactly what its name implies. Blurriness, a question mark, provocation, and yet the question remains. What if this is true? What if, besides color, the mass of an object was indeed captured in a tri-eye atlas passing through the Martian night, bright enough and close enough to be recorded on the surface through image overlay? What does this tell us about its visible brightness, its surface properties, its geometry relative to Mars during the closest approach? These questions lead us to conclusions that are harder to ignore, referring to hot pixels and compression artifacts. Because if the discovery really took place, then the three-eye atlas is brighter, closer, or more reflective than we expected. Brightness in astronomy is almost always an indirect indicator of size or surface area, leading us to the uncomfortable realization that this object may be much larger than the interstellar visitors we have encountered before. Part 3. The Chronology of Silence and Coincidences. The week from October 1st to 7th, 2025 was supposed to bring answers. Instead, it presented questions wrapped in silence and amplified by coincidences. The closest approach occurred on October 3rd at approximately 13 hours Coordinated Universal Time, when 3i Atlas passed within 29 million kilometers of Mars. The observation window lasted several days on both sides, with optimal viewing conditions from October 1st to 7th. Leb's essay set high expectations before the flight. He was counting on data from several Martian orbital probes, including the high-resolution camera of the Martian Reconnaissance Orbiter, as well as Mars Express, and ExoMars Trace Gas Orbiter. He noted that the Perseverance night observation camera could contribute to nighttime sky observations if the mission team decides to allocate time for this purpose. He articulated these observations as critical constraints on the size, composition, and morphology of the 3 Atlas, which could resolve ambiguities that ground instruments could not handle due to distance and observation geometry. The community waited, data did not arrive, and in this silence, a certain story began to form. Over the years, Loeb developed his rhythm, and the audience learned to recognize this pattern. He publishes articles that accumulate anomalies and raise questions before official data releases from space agencies, presenting observations to highlight unlikely coincidences and deviations from basic expectations. He offers both artificial hypotheses and natural ones, viewing them as equally valid for investigation rather than extraordinary claims requiring extraordinary evidence. This approach made him both influential and controversial. His admirers see him as a scholar ready to challenge orthodoxy and ask uncomfortable questions. His critics believe he is prone to motivated reasoning and has a tendency to seek significance in noise. But regardless of your position on Loeb's methodology, his public appearances create anticipation. When he says that observations are close and will resolve key issues, people expect results. When the resolution does not come in the anticipated time, speculations begin to fill the void. The time frame of the U.S. government shutdown added fuel to the already smoldering fire. A partial shutdown of the federal government began on September 30th, 2025, affecting non-essential programs, including some NASA operations, with public relations offices reducing their activities. Non-critical missions were postponed, data release schedules shifted. None of this was unusual or unprecedented. Closures affect public communication more than the core mission operations. Martian orbiters and Perseverance continued to function. Scientific data continued to be collected and transmitted. However, external interfaces, press releases, and curated image galleries that translate raw telemetry into public narratives came to a standstill. Creators and commentators seized the closure as a narrative hook. Why did the closure coincide with the flight of the 3 Atlases? Was it just bad timing? Or was there a deeper reason why the agencies might want to limit public communication during this specific observation period? To clarify, there is no evidence that the closure was planned to suppress data about the 3 in Atlas. Closures occurred due to budget disagreements in Congress, not specific missions, and even during shutdowns, deep space NASA missions continue to operate as they are considered vital infrastructure. The Mars Reconnaissance Orbiter does not shut down. Perseverance continues to take pictures. Data keeps coming to ground stations and archives. What slows down is the labor-intensive process of curating, contextualizing, and releasing this data to the public. The deadlines were arbitrary. However, coincidences, in the context of already heated speculation, become the pillars of conspiracy theories, regardless of whether they deserve such weight. The chain of dissemination worked exactly as intended on social media. Schmauz's publication on Blue Sky spread to Platform X, formerly known as Twitter, where it was quoted and screenshot numerous times. It appeared on Reddit threads related to astronomy and UFOs, where discussion threads grew to hundreds of comments discussing origin and interpretation. Blogs like The Debrief picked up this story, amplifying the meme of the indistinct spot in the image from the Perseverance rover, with headlines straddling the line between factual reporting and provocative presentation. Each stage of enhancement brought new audiences, new interpretations, new layers of speculation detached from the technical details of the original. Within 72 hours of the image's appearance, it achieved a kind of social reality, regardless of whether it represented a genuine discovery or a processing artifact. This stain existed not only in the frames but also in the collective consciousness of all who followed this story. And this collective consciousness began to demand answers that official channels did not provide in the expected time. This scheme has precedents. Uncertainty surrounding Oumuamua lasted several months, with initial observations suggesting a highly elongated, rotating object, and subsequent measurements of non-gravitational acceleration, implying either asymmetric gas emission or, in Loeb's controversial interpretation, a light sail. The absence of detectable clumps or dust led to prolonged debates about whether it was a comet, an asteroid, or something entirely different. Data slowly came in through preprints and peer-reviewed articles, while online communities speculated. sometimes quite actively. In one instance, an interstellar meteorite, which Loeb's team claimed to have retrieved fragments from the Pacific Ocean, followed a similar trajectory. The initial discovery and restoration of the orbit were behind him, followed by expedition planning, oceanic extraction, and laboratory analysis of metallic spirals that Loeb believed exhibited anomalous isotope ratios. Each stage took months, while official confirmations lagged behind Loeb's public essays. Critics challenged interpretations. Attempts at reproduction either failed or confirmed alternative explanations. But the accelerating narrative proved difficult to stop, even as technical objections mounted. Information delay is a common problem in complex observational campaigns and does not imply conspiracy. Data from spacecraft must be downloaded, decompressed, and calibrated. Targeting information must be matched with precise ephemeris for the target. Raw footage must be cleansed of biosignals, filtered, and compiled into sequential images. Spectroscopic data requires wavelength calibration and extraction of one-dimensional spectra from two-dimensional detectors. All of this takes time, especially when observation was not part of the main mission plan and requires special processing. The Martian orbiters have priority tasks related to the geology, atmosphere, and climate of Mars. Observing a temporary interstellar object is an additional scientific opportunity, but it is not the reason for the existence of these spacecraft. The priority in data processing is given to Martian data. Observations of the Object 3 AI Atlas are processed when analysts have time and in the conditions of government closure and overlapping mission stages. This can take days or weeks instead of hours. However, the silence, even if explainable, creates fertile ground for speculation. The analytical conclusion is simple but uncomfortable. The absence of evidence is not evidence of absence, but in a high-stakes observational campaign, the lack of communication functions as testimony to something. Perhaps it is just bureaucratic inertia. Perhaps it is caution before unusual claims, a reluctance to publish preliminary data that may be misinterpreted. Perhaps this is a clash of various communication barriers. Government closure, mission priorities, and internal review deadlines create a gap when the audience expected immediate satisfaction. Or perhaps this is already a boundary of speculation that we must acknowledge, even while resisting it. Perhaps the initial data showed something sufficiently ambiguous or provocative that the agencies decided to verify it 3 times before making any public statement. Not because they are hiding aliens, but because the consequences of a mistake in any direction are enormous. We need to resolve the contradiction in color. Why does the spot appear blue when all other instruments characterizing the 3I Atlas indicate that the light is rich in carbon dioxide, neutral to greenish? This single chromatic discrepancy is more significant than almost everything else in this story because it is quantitatively measurable and reproducible if we access the original frames, serving as a diagnosis of either instrumental artifacts or unexpected physical phenomena. And after we understand color, we need to confront a more complex question. If the leak is true, what does it tell us about the nature of the 3AI Atlas? Part 4. Green that turned blue. The main set of tools described 3I Atlases in shades of green and neutral gray, with a composition dominated by carbon dioxide and a morphology that preferably stretched towards the sun. An image leak from Mars showed a blue color. This chromatic contradiction requires explanation, and this explanation matters because color is physics. The near-infrared spectrograph of the JWST telescope observed 3 comets at the end of September 2025, capturing high-resolution spectra of the coma that showed carbon dioxide as the predominant volatile component. The ratio of carbon dioxide to water was about 8:1, which is significantly higher than in typical comets of the solar system, where water predominates. This discovery proved reliable, was published in a preprint on AR Grief, and confirmed by NASA's Goddard Space Flight Center in their online research. The carbon dioxide coma was intensified by sunlight, with emission levels significantly higher on the sunlit side than on the dark side. Water was present, but in smaller amounts, concentrated in a relatively compact area around the core. Such a composition suggested conditions for the formation of carbon dioxide near isotherms, possibly in remote regions of the planetary system, where carbon dioxide remains frozen while water has already been lost due to earlier heating processes. Either this indicated radiation treatment of surface ice, where cosmic rays and ultraviolet photon emissions from stars preferentially removed hydrogen and volatile substances over geological timescales. In any case, Spectroscopy was unambiguous. It was an object rich in carbon dioxide, not water. The Sphere X Observatory, located in space and operating in the infrared range, was mapping the extended coma of the three-eyed Atlas in early October, detecting carbon dioxide signals extending from the core over distances exceeding 348,000 kilometers. This extended coma confirmed that the emissions were intense and sustained rather than a temporary phenomenon or a local jet emission. The morphology showed broad emissions corresponding to sublimation on or near the surface caused by solar heating, which was exactly what was expected from a natural comet reacting to increased insolation as it approached perihelion. Sphere X data complemented JWST spectroscopy, providing spatial context for composition measurements. Together, these observations confirmed that the three-eyed Atlas was surrounded by a massive extended shell of carbon dioxide and dust, visible from a great distance within the inner solar system. Images from the Hubble telescope showed a morphology that was unusual but not unprecedented. The most striking feature was the scattered sunlight, an anti-tail that preferentially pointed towards the sun rather than away from it. Classic comets display anti-solar tails made of dust and structures pushed outward by solar pressure and solar wind. Anti-tails, which appear to point towards the sun, arise from the geometry of observation and the distribution of dust particles along the orbital path of a comet. When we see a comet almost from the side, the dust particles ejected earlier in its orbit may seem directed towards the sun, although physically they are behind. The three-eyed Atlas demonstrated this geometry, but with an extreme aspect ratio. Loeb and his colleague Evgeny Kito noted that the solar stretch was about 10 times longer than its width, creating a needle-like structure in the processed images. The modeling suggested that it reflects isotropic radiation from the hot sunlit side, with dust and gas preferentially ejected from areas directly illuminated by the sun. The geometry was strange, but it could be modeled within the physics of natural cometary activity. What color should one expect from a coma saturated with carbon dioxide? The situation is a bit more complicated here. Pure gas has no color in the visible spectrum. We perceive gases through emission or absorption lines, not through scattered continuous light. When we look at a comet, we see sunlight scattered by dust particles in the coma. The color of this scattered light depends on the size of the particles, their composition, and the scattering efficiency related to the wavelength. Carbon dioxide alone does not give a green color. Nevertheless, many comets appear green in images due to the emission of diatomic carbon, C2, which produces strong green emission lines around 510 nanometers when excited by ultraviolet solar radiation. The three-eyed comet did not show significant C2 emission, at least in the published spectra to date. The expected color from the scattering of light by dust in a coma rich in carbon dioxide in the absence of strong emission lines will be neutral or slightly reddish, corresponding to the inner color of sunlight considering the properties of dust particles. Some composite visualizations may show a faint green tint as processing algorithms enhance weak emission features. However, a bright saturated blue color is not predicted, raising questions about the physics of the blue blur caused by mass leakage. Blue light scatters more efficiently than red on very fine particles. This explains why Earth's sky is blue and why distant mountains appear blue through atmospheric haze. During Rayleigh scattering, which dominates when particle sizes are much smaller than the wavelength of light, a blue component of scattered light could be observed if the three-eyed comet contained an unusual population of very fine dust or aerosols, and if the observation geometry from Mars emphasized frontal scattering through this material. But JWST and Sphere-X reported no signs of a predominant population of submicron particles. The size distribution of dust particles derived from these observations was consistent with typical cometary dust, ranging from submicron to millimeter sizes, with most of the mass in larger particles. There is no obvious physical reason why a coma saturated with carbon dioxide could appear blue in scattered sunlight. Thus, we return to explanations related to instruments and data processing. A non-astronomical camera, like the Mastcam Z, designed for daytime geology under Martian lighting, uses color calibration procedures optimized for these conditions. The surface of Mars is mostly red due to iron oxide dust. The atmosphere scatters light with a distinct salmon hue throughout the day. Mastcam Z's white balance algorithms are adjusted to convey colors that geologists can interpret. When you direct the same instrument at a faint astronomical target at night, you go beyond its original purpose. Color calibration may simply be irrelevant. If image processing is based on warm, reddish lighting and then encounters a relatively neutral source, color correction can lead to excessive adjustment, shifting the visible color towards blue. This is a rather dull explanation, but probably the most plausible. There is another hypothesis, although it is more speculative, which considers the aggressive suppression of noise or incorrect weighting of channels during the image overlay process. If the red channel had a higher noise level compared to the blue and green in individual frames, the analyst might decide to reduce the weight of the red to avoid false signals. Either if the frames were made using various combinations of filters and then compiled into an RGB image, the choice of filters might not match the true colors. Mass cam filters have narrow ranges that do not correspond to standard RGB wavelengths. The combination of filters to create a visually intuitive color image requires assumptions about how to weigh each channel. Different assumptions lead to different colors, especially for weak objects with low signal-to-noise ratios. This hypothesis about the incorrect weighing of channels can be tested if we gain access to the original data. But without such access, it remains mere speculation. The least likely hypothesis, but worth mentioning as it is discussed, concerns a reflective metallic surface. If the three-eyed atlas is not a diffuse coma, but a compact structured object with a reflective surface, some assumptions about white balance could distort the color towards blue under the Martian night sky. Metals have a relatively uniform reflective ability in the visible spectrum. They do not appear blue unless coated or textured in a way that preferentially reflects shorter wavelengths. Stainless steel looks gray, aluminum looks gray, polished titanium looks gray. But if the image processing anticipated a reddish light source and encountered neutral reflectivity, color correction could lead to a blue tint in the processed result. This is mechanically possible, but requires the simultaneous fulfillment of two conditions. First, the three-eyed atlas must be a reflective structure, not a diffuse coma. Secondly, the processing must have incorrectly applied color calibration in such a way as to produce a blue artifact from a neutral source. The combination of these requirements makes this hypothesis weak, but not impossible. Ultimately, the conclusions remain sharp and unpleasant. We cannot make physical conclusions based on a color stack processed using unknown methods and presented outside formal verification channels. The color mismatch between the blue spot and the neutral or greenish representation from spacecraft is a troubling signal that requires reproducibility based on original frames. We need multiple independent analysts processing the same data with transparent and documented methods. We need multi-channel photometric observation from Muscom Z if these ranges have been recorded, which will allow us to restore the spectral energy distribution and determine whether the blue shade is real or an artifact. We need cross-checks from other Martian objects if any data was received during the flyby window, and it must be honestly admitted that without these confirmations, the blurriness speaks more about the image processing than about the object. But, setting color aside, let's suppose for a moment that the discovery is indeed true. Let's assume that Muscom Z has indeed captured three eyes of the atlas passing through the Martian night at the predicted coordinates, faint yet present, visible only through careful composition, but undeniably existing. What can this mean? This question leads us into uncomfortable territory, as brightness in astronomy almost always depends on either size or reflectivity. And if the three eyes of the atlas are bright enough to be detected on the Martian surface from a distance of 29 million kilometers, then they are either larger, closer, or more reflective than we might expect from an interstellar comet, leading us to consequences that cannot be ignored. Part 5. What a leak implies if it is real. The brightness of the parent surface is not a random observation. It is a physical constraint linking luminosity, distance, and the geometry of observation into a dense web of consequences. If the Muscom captured three eyes of the atlas through layered frames, then the object was bright enough, vast, or favorably positioned for a non-astronomical camera to distinguish it from the Martian night sky. This statement contains several possible truths, and we need to carefully delineate them. The conservative interpretation suggests that the folded signal represents a comet's tail, an extended envelope of gas and dust, which has already been confirmed by JWST and Spherex. Comet tails can be remarkably diffuse, spreading light across vast angles and appearing faint per unit area, even despite high integrated brightness. but they can also demonstrate improvements in surface brightness in certain directions, especially in the geometry of direct scattering, when sunlight, reflecting off dust particles, is preferentially directed towards the observer. The geometry of the flyby around Mars positioned Perseverance on a favorable line of sight to observe the solar hemisphere of the three-eyed atlas. This is the area where JWST recorded an enhanced release of carbon dioxide, and Hubble observed an elongated anti-tail feature. If Mars was in the direction of direct scattering, the visible brightness of the tail could have been significantly higher compared to what observers on Earth saw. This fully aligns with the natural physics of comets. This does not require exotic composition, structured surfaces, or engineering properties. Only the geometry and optics of dust performing their functions. But in this interpretation, there is tension. Muscam-Z is not a sensitive instrument for weak, extended sources. This is the noise of the detector. Red noise and dark current optimize for short exposures in bright light, not for long integrations of weak, diffuse objects. Even when combining images to highlight the extended comet from the noise, its surface brightness must exceed a certain minimum per pixel. If the coma of the object, Three Eyes of Atlas, was as diffuse as suggested by Spherex mapping, spreading carbon dioxide over hundreds of thousands of kilometers, then the surface brightness at a distance of Mars must have been extremely low, probably below the practical detection limit of Muscam-Z, even with aggressive stacking. The fact that the signal has appeared, if genuine, indicates either that the coma was more concentrated than large-scale mapping showed, or that we are seeing something with higher internal brightness than ordinary diffuse coma. Speculative interpretation suggests the presence of a reflective or structured surface rather than a diffuse gas shell. If the Three Eyes of Atlas has a compact, highly reflective shell, possibly metallic, its visible brightness will change very differently than that of a comet's coma. A reflective sphere or ellipsoid effectively scatters sunlight from its illuminated hemisphere, concentrating brightness in a small angular area rather than spreading it over a large diffuse shell. The brightness of such an object, even at a distance of 29 million kilometers, can exceed the brightness of a diffuse coma by orders of magnitude. This would make its detection possible with a tool like Muscam-Z, despite unfavorable observation conditions. Geometry here is of immense importance. If Mars observed the Three Eyes of Atlas at a favorable angle of phase, where the mirror reflection directed sunlight to the rover's position, the brightness could sharply increase. Эта интерпретация требует отказаться от предположения, что три глаза Атласа в основе своей является кометой, и принять возможность того, что это нечто совершенно иное, нечто с инженерными, а не геологическими свойствами на своей поверхности. Loeb actively questions the size in his medium essays, claiming that the core diameter is 5 kilometers or more based on brightness constraints and measurements of non-gravitational acceleration. His argument connects several observations in a chain of conclusions. The absolute magnitude of an object, the brightness it would have at standard distances from both the sun and the observer, limits the product of size and reflectivity. If we assume a typical comet albedo of about 4%, which means the surface reflects 4% of the incoming sunlight, brightness measurements imply a diameter of several kilometers. The non-gravitational acceleration, how the orbit of Three Eyes of Atlas deviates from purely droplet motion due to the pull caused by gas ejection, provides an independent constraint. For this level of ejection, derived from the brightness of the coma, a smaller mass implies a higher acceleration. The observed acceleration is relatively weak compared to the brightness of the object Three Eyes of Atlas, which in Loeb's analysis indicates its greater mass. The high mass, combined with the typical density of comets, implies a significant volume, justifying the estimate of 5 kilometers. He translates this into 33 billion tons, a figure meant to convey the scale of what we can observe. If the Three Eyes of Atlas indeed has a diameter of 5 kilometers, it places it in a different category compared to previous interstellar visitors. The object Oumuamua measured about 100 to 200 meters along its longest axis, which is relatively small for comets or asteroids. The object Boris measured about half a kilometer in diameter, comparable to small comets in the solar system, but not remarkable in size. An interstellar object 5 kilometers in size would be significantly larger, suggesting that we were incredibly lucky to intercept such a massive traveler, or that large interstellar objects occur more frequently than indicated by the statistics of the two previous discoveries. This creates a paradox of detection speed. If 5-kilometer-sized objects pass through the inner solar system regularly enough for us to catch one in just a few years of observation, then where are all the smaller ones? The fear of detection leans towards finding large, bright objects rather than small, dull ones, so the population of interstellar visitors about 100 meters in size should significantly exceed the population of those a kilometer long. We had to see dozens of objects the size of Oumuamua before catching even one giant the size of the three-eyed Atlas. The fact that we did not do this indicates either an error in assessing size or that the statistics of interstellar objects differ significantly from what was assumed, or that the three eyes of Atlas is not a random member of the statistical population, but represents an object chosen for specific properties. The role of the Martian orbiter becomes critically important for resolving these uncertainties. Liob, in his essays before the flight, claimed that the high-resolution camera of the Martian Reconnaissance Orbiter offers unique capabilities due to its spatial resolution at the distance of the three eyes of Atlas. The high-resolution Mars imaging camera captures the surface of Mars at a resolution of approximately 30 centimeters per pixel from low orbit, but when aimed at an object 29 million kilometers away, the effective pixel scale increases to about 30 kilometers per pixel. This may seem useless for resolving details, but it is actually useful for diagnosing the brightness of a point source. If the three eyes of Atlas were a compact reflective object rather than a diffuse coma, and if it were bright enough, it could saturate individual pixels of a high-resolution image or create a measurable light scattering function, distributing light across several pixels. By measuring which pixels light up and how brightly, analysts could determine whether the signal comes from an extended diffuse source or a compact object with high surface brightness. This is a delicate task that requires careful adjustment and modeling, but, in principle, the data exists or should exist if the high-rise spacecraft truly observed the object during its flyby. The discovery of the surface of Mars, if it indeed took place, raises the stakes for these observations made by orbital devices. If the Perseverance camera, despite its relative primitiveness, was able to capture Atlas's three eyes through image overlay, then HiRISE, with its more advanced optics and filming capabilities, should have certainly captured it if properly aimed. The silence from the HiRISE and other Martian orbital vehicles immediately after the closest approach carries information. Either they did not observe the object, which would be surprising given the careful preparation and public expectation, or they did observe it, and the data is still being processed and verified before publication. It is also possible that they observed something ambiguous, provocative, or complex, prompting agencies to delay public statements until they understood what they had seen. None of these possibilities prove anything about the nature of Atlas's three eyes, but they all point to the same conclusion. The flight of Mars was not a routine observation of a comet. Something about this event elevated it above standard operating procedures. We stand on the brink of discoveries. A leak, if it exists, turns from a curious anomaly into substantial evidence that the three eyes of Atlas are not what we thought they were. But before crossing this threshold, we need to step back and examine the object itself, regardless of any single controversial image. What do the commonly accepted scientific observations tell us? What patterns emerge when we consider Atlas's three eyes not as an isolated mystery, but as a third interstellar visitor that we have been able to study? Strangeness in the orbital plane, chemistry that defies solar system templates, polarization measurements beyond known families, morphology stretching towards the sun in need of explanation. These are not leaks, rumors, or processing artifacts. These are published, peer-reviewed, or at least pre-printed observations from flagship instruments managed by agencies that have no incentive to create controversies. And when we put them together, they paint a picture that deeply disturbs, regardless of whether you believe in hypotheses about artificial origins. It depicts an object that should not exist according to our basic expectations of what interstellar space sends us. This object and its consequences are what we now turn to. Part 6. The Riddle of 5 Degrees. Precision or chance. Imagine throwing a dart at a globe from the other side of the room with your eyes closed. Now imagine that this dart, against all odds, lands within 5 degrees of the equator. It's not quite a precise analogy, because at least you aimed in the general direction of the globe. 3 objects called I-Atlases arrived from interstellar space without any particular reason for choosing our planet. They had no prior knowledge of Earth's orbital position and were not connected to the flat plane defining the architecture of the solar system. Nevertheless, their trajectory deviates by only 5 degrees from the ecliptic, the plane in which Earth's orbit and most other planets lie. A scholar named Heavylobe calculated the probability of such a coincidence randomly and arrived at a figure of about 0.2%, or roughly 1 in 500. This figure is based on assumptions about how interstellar objects should be distributed if their appearances are truly random. One should regard this calculation with a certain degree of skepticism, as the effects of choice and the statistics of small numbers can significantly inflate the perceived probability. Nevertheless, even with conservative assumptions, this coincidence is striking enough to demand an explanation. The orbital parameters of objects are publicly available and independently verified through several tracking systems. The I-atlases move in a retrograde orbit, meaning they move in the opposite direction to the planets around the Sun. The tilt, the angle between their orbital plane and the ecliptic, is approximately 4.5 to 5 degrees, depending on which orbital solution you consider. In comparison, most comets of the solar system from the Oort cloud arrive on orbits with random inclinations, varying from 0 to 180 degrees with approximately uniform distribution. Long-period comets do not show a preference for the ecliptic, as the Oort cloud is a spherical distribution of icy bodies surrounding the Sun at vast distances. Interstellar space, according to any reasonable models, should be even more isotropic. Objects ejected from other planetary systems have no memory of our system's orientation. Their arrival directions should uniformly cover the entire sky. Therefore, a trajectory close to the ecliptic is statistically unlikely. However, unlikely does not mean impossible, and 5 degrees is not 0. Let's precisely define what geometry means. Arrival from interstellar space, exactly in the ecliptic plane, would be an extraordinary event requiring unnatural explanations. A 5-degree deviation from the ecliptic is unusual but not absurd, placing the trajectory of the I-atlases in a broad band around the planetary disk of the solar system rather than randomly oriented in 3-dimensional space. This distinction matters, as our intuition about the probability of coincidences is generally poor. People are pattern recognition machines, and we more often see design in randomness than randomness in design. A 5-degree tilt may represent the end of a statistical distribution, a single arrival out of hundreds that coincided with the direction simply because probability allows rare events to occur, or it may indicate something else. A trajectory designed to maximize the chances of encountering planets while maintaining an approach angle that minimizes Earth's chances of observation at the moment of initial detection. The forehead formulates it as a hypothesis about the delivered trajectory, and it is worth considering the logic, even if we clearly define it as speculation. If you were designing a mission to study a planetary system from interstellar space, you would want your probe's trajectory to pass close to several planets in one pass to maximize scientific results for given energy costs. The ecliptic of Earth includes not only Earth, but also Venus, Mars, Jupiter, Saturn, and other large worlds located within a few degrees of a single plane. The trajectory aligned with this plane allows for natural encounters with multiple targets without the need for course adjustments. The Tri-I-Atlas probe passed by Venus at a distance of approximately 0.3 astronomical units. On September 5, 2025, a close approach occurred, causing significant heating and likely triggering enhanced gas emissions. It passed by Earth at a distance of 1.23 astronomical units on September 27th. Mars was reached on October the 3rd at a distance of 0.20 astronomical units. This close approach caused a leak of images from mass cameras and an expanded observational campaign. It is planned that the probe will pass by Jupiter on March 16, 2026, at a distance of approximately 1.9 astronomical units. These are 4 planetary meetings in 6 months, a trajectory that efficiently passes through the inner solar system. Statistics bring us back to mundane data. Considering only the 2 previously discovered interstellar objects, 1 Oumuamua and 2 Borisov, we do not have enough samples to establish what the norm looks like. Oumuamua entered the solar system at an angle of about 28 degrees to the ecliptic, clearly deviating from the plane, but not perpendicular to it. Borisov entered at an angle of about 44 degrees, which is also significant but not random in relation to the architecture of the solar system. 2 objects are not enough to determine the distribution. 3 is hardly better. Perhaps we are witnessing the beginning of a pattern where interstellar objects prefer to arrive within 30 or 40 degrees of the ecliptic for reasons we do not yet understand, possibly related to galactic dynamics or the structure of the local interstellar medium. Or it could just be a coincidence, three dice thrown that happen to land in a visually striking arrangement with no hidden reason behind it. To distinguish these possibilities, it is necessary to detect dozens or hundreds of interstellar visitors and statistically map their arrival directions. We are far from such a sample size. However, the hypothesis about the delivered trajectory gains strength when you overlay a 5-degree alignment on other anomalies we are about to investigate. When considered in isolation, the orbit close to the ecliptic is intriguing, but not a decisive factor. In combination with the timing that provides close passes to Venus, Earth, Mars, and Jupiter in rapid succession, we add solar morphology that concentrates light and dust towards sunlight rather than distributing them isotropically. We mix chemistry that does not match the cometary patterns of the solar system, adding measurements of polarization that go beyond known comet families. And it all concludes with a possibility that has yet to be confirmed, but intriguingly suggests that the object has a higher surface brightness than predicted by diffuse coma models. Each individual anomaly can be explained, but the combination of several unlikely traits in one object raises doubts about ordinary explanations. This combination is what Lobus arrived at in his public essays, and we need to honestly confront it, even if we ultimately reject the hypothesis of artificial origin. The alignment with the ecliptic carries another meaning that should be stated clearly. If the trajectory of the three-eyed atlas was chosen and not random, then its approach vector was also chosen. The object arrived from a specific region of the sky, with a particular ascending straight line and declination that correspond to a specific direction in galactic coordinates. If this were an interstellar probe intentionally sent to our solar system, the launch point would be along this arrival vector, somewhere in the deep past and at a significant distance, from where the object's path is extrapolated back into interstellar space. Analysts calculated this reverse vector, the point of origin, adjusted for the rotation of the galaxy and the movement of the sun through the local interstellar medium, is generally in the direction of the constellation Triangulum, but with enormous uncertainty in positioning, as we do not know exactly when the object began its journey. If it has been moving for 10,000 years at a speed of about 29 kilometers per second relative to the sun, then it originated approximately 2.9 light-years away from us, fitting well within the nearest stellar neighborhood. If he moved for 1,000,000 years, the point of origin would shift significantly due to the differential rotation of the galactic disk. Not knowing the launch date, we cannot pinpoint the source exactly, but we can say that the trajectory does not point to any particularly interesting star system that we have identified as having planets or unusual properties. The origin is unremarkable, at least considering our current data, which means that either the source is something we did not recognize as interesting or the trajectory was not direct from launch to arrival. Geometry is just one part of an overall dubious set. In isolation, it is provocative, but not conclusive. Combined with 6 other anomalies cataloged by Lobus, it becomes part of a pattern that seriously considers the possibility that the three-eyed atlas is not a typical interstellar comet, if such a thing even exists. A set of statistical improbabilities is what we will consider next, and it is here that arguments for something extraordinary become harder to dismiss, despite discussions about randomness and choice effects. Because when you have 7 independent anomalies, each unlikely on its own, but all present in one object, you are no longer talking about simple luck in a dice throw. You are talking about either a fundamental misunderstanding of the behavior of interstellar objects or an object designed to behave differently than nature suggests. The 7th part is a statistical improbability stack. The report on the approach to Mars by Unveils lists 7 specific anomalies that distinguish the trio, Three-Eye Atlas, from standard expectations of what an interstellar comet should look like. This is his perspective, based on the search for evidence that could support the theory of artificial origin. Leading astronomers studying the same data would focus on different features, or interpret the anomalies as an expansion of our understanding of comet diversity, rather than a challenge to natural hypotheses. However, Lobus's list provides a useful structure for analyzing what makes Three-Eye Atlas truly strange, whether you interpret this strangeness as artificial or simply exotic. The immediate positioning relative to the ecliptic, which we have already discussed, and the low odds in Lobes's calculations may be explained by selection effects or small number statistics, but are noteworthy enough to attract attention. Time adds weight to the geometric anomaly. The 3-eye atlas not only approached the ecliptic plane, but it followed a trajectory that ensured close encounters with Venus, Earth, Mars, and Jupiter over 6 months from September 2025 to March 2026. This clustering of planetary flybys is not physically impossible within natural scenarios, as any trajectory roughly aligned with the ecliptic will inevitably pass near several planets, since they rotate in the same plane. But the specific geometry and temporal parameters that ensure 4 meetings in quick succession require a special arrival, speed, and direction. Most trajectories aligned with the ecliptic would pass above or below the orbits of planets, intersecting the plane at points where planets are absent. The fact that the intersection of 3-eye atlas coincided with several positions of planets suggests either a fortunate coincidence or selection. Lobb insists on the last point. Skeptics advocate for the first, noting that we are more likely to detect interstellar objects passing near Earth because our detection systems are biased towards finding objects that approach. Both arguments have their merits, and distinguishing between them requires population statistics that we currently lack. The sun will shine is a place where explaining everything becomes more complex from the perspective of simple geometry. Observations from the Hubble telescope revealed the morphology of 3-eye atlas in stunning detail in mid-September 2025, capturing images that showed a blurred elongation primarily directed towards the sun rather than away from it. Typical comets display antisolar tails, structures pushed outward by solar pressure, and the interaction between the solar wind and the ionized coma. Some comets also show antitails, structures pointing forward that appear due to the geometry of observation when we see the edge of the comet's dust trail. The feature of the comet Tri-Eye Atlas was described in Hubble's analysis as radiation from the daytime side and a weak antisolar tail, corresponding to an anisotropic emission of material from the solar side. Lobb and his colleague Evgeny Kito emphasized that at the moment of observation with the Hubble telescope, Earth was only 10 degrees from the line Sun, Tri-Eye Atlas, meaning we were observing the object almost from a side angle. The solar projection measured by them stretched about 10 times longer than its width, indicating a highly elongated structure, considering the effects of projection. This is unusual, but not unprecedented in literature about comets. Some comets exhibit a strong anisotropic outflow due to active regions concentrated in specific parts of the nucleus. The interest of the 3-eye atlas case lies in the combination of solar amplification, extreme size ratios, and chemistry dominated by carbon dioxide, which we will discuss now. A coma dominated by carbon dioxide is perhaps the most fundamental anomalous feature, as it was identified using the spectroscopy of the James Webb Telescope, which is considered the gold standard for composition analysis. Spectra in the near-infrared range obtained at the end of September showed that carbon dioxide emission lines dominate the spectrum, with a carbon dioxide to water ratio of about 8 plus or minus 1. This is significantly higher than typical comets of the solar system, where water usually predominates and carbon dioxide makes up from a few percent to 30% of the total volatile content. In the solar system, there are objects with high carbon dioxide content, such as Comet 29Pa Schwarzmann-Wachmann, known for its outgassing caused by carbon dioxide, but they are rare. The high ratio indicates that Tri-Eye Atlas formed in an environment where carbon dioxide remained frozen while water ice was depleted, either because it formed outside the carbon dioxide ice line in its parent system or due to surface processing by cosmic rays and ultraviolet photons that preferentially removed water over geological timescales. Both scenarios are physically plausible, but they impose limitations on the origin and history of the object, which are hard to verify without knowing from which star system it came and when it was ejected. The nickel-rich composition becomes the most contentious aspect. In his essay titled Extreme Nickel Production, Lobb highlighted spectroscopic detections of neutral nickel lines at various heliocentric distances from approximately 3.14 astronomical units to 2.14 astronomical units. The emission of iron, which is usually observed alongside nickel in the spectra of comets, was absent below about 2.64 astronomical units. Lobb interpreted this as a sign of an abnormally high nickel-to-ion ratio in the ejected material, calling it extreme and exceptional compared to the comets of the solar system. The discovery of neutral nickel and ions in comets is a relatively recent finding, with the first data published only in the last 10 years. The presence of metallic atoms in the atmospheres of comets raises questions, as the evaporation of refractory metals requires high temperatures far exceeding those reached even near perihelion. The main explanation for this phenomenon is related to the photodissociation of organometallic molecules, or the sublimation of metal-containing particles heated by solar radiation. However, it remains unclear why nickel predominates over ion in the coma of Comet 13 Atlas, given that ion is more common in typical cosmic chemistry. The forehead claims that this ratio is unusual enough to consider the possibility of unnatural origin, particularly industrial alloys where nickel is deliberately enriched. This assumption is based on incomplete data, but is not a fabrication. Spectroscopic measurements are real, even if their interpretation is controversial. Extreme negative polarization refers to a more specialized field. Polarimetry measures how much light from an object is linearly polarized, meaning the electric field oscillates predominantly in one direction rather than randomly. Comets polarize sunlight, scattering it on dust particles, and the degree of polarization depends on the size, shape, composition of the particles, and the geometry of observation. Polarization is a function of the phase angle. The angle between the sun, the comet, and the observer follows a characteristic curve, allowing astronomers to classify comets into families. The polarimetric curve of Comet 13 Atlas, measured at various phase angles during its approach, showed parameters different from the known families of comets in the solar system. In particular, it demonstrated greater negative polarization at small phase angles than typical comets, although still within values that natural dust particle models can reproduce when considering the unusual properties of the particles. The preliminary publication on polarimetry, which reported these measurements, presented them as an extension of the known variety of cometary dust rather than an indication of artificial origin. However, diversity has its limits. If every interstellar object we discover exceeds the range established by the thousands of comets in the solar system, at some point we must ask whether the expansion of diversity is doing too much work in the explanation. The tension between brightness and acceleration is more subtle and requires understanding how non-gravitational forces affect comet orbits. When a comet emits gases, the expelled gas and dust carry away momentum. If the gas emission is anisotropic, concentrated on one hemisphere or in certain directions, the reaction force acts like a small rocket engine, slightly diverting the comet from a pure Keplerian orbit. This non-gravitational acceleration is inversely proportional to mass at a given gas ejection speed. Small comets experience greater deviations from gravitational trajectories than large comets with the same level of activity. By measuring the non-gravitational acceleration and assessing the gas release speeds by the brightness of the coma, one can constrain the mass of the comet and thus its size, assuming density. Atlas 3I's demonstrates relatively weak non-gravitational acceleration considering its brightness, which in forehead analysis implies high mass. High mass may indicate either large size or extraordinarily high density. Lobb asserts that the size is indeed large, estimating the diameter at 5 kilometers. Critics note that the relationship between the brightness of the coma and the mass of the nucleus is not straightforward, as brightness depends on dust production, which does not limit the content of volatile substances or the total mass of the nucleus. There is tension, but its resolution depends on what uncertainties you are willing to accept and which assumptions you prioritize. 7 anomalies. Each of them can be individually explained within the framework of natural processes if exotic conditions of formation, unusual compositions, or rare but plausible geometries are allowed. Ecliptic alignment may be random. The time frame of the collision with the planet may result from selective displacement. The glow towards the sun could be an anisotropic emission observed from the edge. The prevalence of carbon dioxide may indicate the formation near the icy carbon dioxide line or radiation processing. The behavior of nickel in relation to iron may be the result of unusual photochemistry of the grains. Negative polarization can expand the natural diversity of the dust's properties. Weak acceleration, despite brightness, may indicate high mass or uncertain ratios of dust and gas. None of these explanations is unlikely on its own, but when you require each to be true simultaneously for the same object, you stack coincidences into a tower that begins to look shaky. Loba's rhetorical strategy is to emphasize this tower, arguing that the collection of anomalies challenges the natural hypothesis beyond what Occam's principle comfortably allows. Mainstream astronomers argue that our selection consists of only 3 interstellar objects, noting that diversity in nature is vast and that extraordinary claims require extraordinary evidence. Both opinions have the right to exist, and that is why the Atlas of Three Eyes has become such a point of tension in the ongoing discussions about how to interpret ambiguous data. The issue with nickel deserves separate study, as it is an anomaly that most directly evokes associations with industrial or engineering chemistry. If you are looking for irrefutable evidence that the Atlas Three Eyes may be unnatural, the ratios of metals should be your focus, and this is what we will concentrate on next, as the chemistry of this object is not just strange, it is diagnostic. Part 8. The problem with nickel. Nickel without iron resonates with the basic characteristics of industrial stainless steels, where nickel is intentionally added to enhance corrosion resistance and mechanical properties. This comparison belongs to Avalob, who clearly articulated it in his essays and was picked up by publications like The Debrief in their coverage of Atlas Three Eyes observations. This is a provocative frame, and it demands that we separate what observations actually show from what they may imply. Lioba's essay on nickel production in extreme conditions briefly outlines the results of spectroscopic observations covering the approach trajectory of Comet 3I Atlas, starting from 314 astronomical units, where neutral nickel emission was first detected, to 2.14 astronomical units, when the object reached perihelion. Nickel appeared throughout this range, manifesting as characteristic emission lines in the visible spectrum from 5,000 to 6,000 angstroms. These lines arise when neutral nickel atoms in a coma absorb ultraviolet solar photons and re-emit visible light at specific wavelengths determined by the atomic structure of nickel. The iron, which has its own emission lines in similar wavelength ranges, was absent in the spectra obtained below approximately 2.64 astronomical units. This may mean that iron was never present in significant amounts in the material evaporating from the comet's core, or that iron and nickel are produced or released by various mechanisms activated at different heliocentric distances. To unravel this mystery, let us turn to the available chemistry at the discussed heliocentric distances. Solar heating raises the surface temperature of the comet's nucleus to values between 200 and 300 kelvins, depending on albedo and thermal inertia. These temperatures are high enough for the sublimation of water ice, carbon dioxide ice, carbon monoxide ice, and various other volatile substances that make up the cores of comets. However, they are far from sufficient for the direct evaporation of metallic nickel or iron. Nickel melts at a temperature of 1,728 kelvins, while iron melts at 1,811 kelvins. The evaporation temperatures are even higher, so when we observe neutral atoms of nickel and iron in the atmospheres of comets, they do not come from the evaporation of massive metal from the surface of the nucleus. Most likely, they originate from organic metallic molecules, metallic atoms linked in organic structures, or from fine dust particles containing metallic phases that are heated to much higher temperatures than the core itself due to the absorption of solar radiation. The detection of nickel and iron emissions from comets is a relatively recent event, first convincingly reported in 2019 based on observations of interstellar comet 2I Borisov and later confirmed in several comets of the solar system. До этих открытий существовало мнение, что рефрактерные металлы не должны появляться в кометарной коме из-за слишком низких температур. Это открытие заставило переосмыслить химию комет и открыло вопросы о механизмах доставки металлов, которые все еще активно обсуждаются в научной литературе. Most models suggest the photodissociation of molecules like nickel carbonyl or iron carbonyl, which can sublimate at much lower temperatures than pure metals and then break down in sunlight, releasing metal atoms. Another possibility is that submicron particles containing metallic phases are heated to very high temperatures by absorbing concentrated solar flux, reaching thermal equilibrium temperatures that allow the metal to sublimate from the surfaces of the particles. The behavior of Comet 31 Atlas is of interest not because of the presence of nickel, which has been observed in other comets, but because of the ratio of nickel to iron and how this ratio changes with distance from the sun. Cosmic abundance is the relative amount of elements produced in the process of stellar nucleosynthesis and found in the universe, showing that iron is about 17 times more abundant than nickel. Iron is the most abundant heavy element in the universe after oxygen, silicon, magnesium, and a few others. Nickel is relatively common, but noticeably less so than iron. The materials of the solar system generally reflect cosmic abundance unless influenced by specific processes. Meteorites, which are samples of the solid materials from which planets and asteroids formed, show a ratio of iron to nickel that generally corresponds to cosmic values. Comets, being primitive bodies formed in the cold outer regions of the protoplanetary disk, must also reflect cosmic or near-cosmic metallic ratios in their composition. If there is nickel without iron or insignificant excess of nickel compared to iron in 31 Atlas, several possibilities arise. Firstly, the parent material from which the comet formed could have been chemically separated, leading to an increase in nickel content compared to iron. This could happen if the conditions favored the condensation of nickel-containing phases, leaving iron in gas or other phases that did not join the core. Secondly, the mechanisms that release metallic atoms in the coma may operate differently for nickel and iron, possibly due to their association in various molecular carriers or granular phases that sublimate or photodissociate at different temperatures or solar flux levels. Thirdly, the observational effects of choice can make nickel more noticeable than iron in the ranges of wavelengths and sensitivities of the spectrographs used, creating a visible, anomalous excess that does not reflect the actual composition. Or fourthly, the material does not match the natural composition of the comet, but instead reflects processing or engineering that deliberately altered the metal ratios. The fourth option is considered a viable hypothesis, pointing to industrial alloys on Earth, where nickel is added to iron to create stainless steels, superalloys, and other materials with enhanced properties. The author does not claim that the 31 Atlas is made of stainless steel welded in some alien factory. His argument is more subtle. If the object were an engineering structure designed for survival during interstellar travel and close approaches to the sun, its outer layer could be covered or made from materials chosen for heat resistance, radiation durability, and mechanical strength. Such materials could have a nickel to iron ratio different from cosmic abundance, as they were optimized for performance rather than reflecting the natural distribution of elements in their original environment. When such materials are exposed to solar heating, the released atoms can transfer pre-planned ratios to a comet, where spectroscopy can identify them as anomalous compared to natural expectations. This is merely a hypothesis, clearly marked as such, but it can be tested. If the three-eyed Atlas continues to demonstrate rich nickel radiation as it passes perihelion and begins its outbound journey, and if a higher signal-to-noise ratio in spectroscopy confirms the absence or insignificance of iron, it will strengthen the arguments about its unusual composition. If future observations detect the presence of iron at various distances from the sun or at different angles of phases, it will support the interpretation that nickel and iron come from different sources with varying temperature thresholds. If laboratory studies of similar materials, organometals, or metallic grains subjected to ultraviolet light and thermal cycling can reproduce the observed radiation patterns, it will provide a natural way to explain. The data is not yet final, explaining the coexistence of exceptional frameworks with the caution of the mainstream. There is a connection to Loeb's early work on E1, the interstellar meteor from which his team extracted fragments at the bottom of the Pacific Ocean. The analysis of metal spirals found during this expedition claimed they discovered unusual elemental ratios in the isotopic signatures, which Loeb interpreted as evidence of artificial origin, or at least an extraterrestrial source. Independent laboratories studying similar spirals disputed these interpretations, claiming that the ratios correspond to terrestrial pollution or misidentified cosmic spirals formed by the natural ablation of meteoroids. Debates around the IM-1 findings made some community members skeptical of Loeb's claims about nickel behavior in the three-eyed Atlas, seeing it as part of a pattern where he finds industrial signs in data that others interpret as natural variations. This skepticism is justified, but it does not diminish the spectroscopic measurements that come from established observatories and are published for public discussion. Future observations may resolve the nickel issue. A higher signal-to-noise ratio in spectra over a wider range of distances from the sun and phase angles will help determine whether the nickel-to-iron ratio is constant or varies with observation geometry. Observations at several wavelengths, including ultraviolet spectra, can capture lines of ion radiation that may be too weak to register in invisible light. Laboratory measurements of metallic emissions from analog comet materials under controlled conditions will calibrate the expected ratios from natural processes, while comparative studies of other comets, both from the solar system and interstellar space, if we are lucky to observe more, will help determine whether the behavior of the three-eyed atlas is unique or part of a broader population of nickel-rich objects. At this point, none of these observations are complete, meaning the problem with nickel remains open, unresolved, and provocative. Oddities in spectroscopy combine with oddities in morphology, creating a complex picture that is harder to explain than each anomaly individually. The problem with nickel indicates that something chemically unusual is being ejected from this object. The solar flux tells us that there is something geometrically strange about how the matter is expelled and distributed. Together, they point to either exotic physics that we do not fully understand, or engineering solutions that we are not yet ready to seriously consider. The solar flow and its consequences are what we will address next, as this morphology is not just strange, it is directed, and direction in nature usually requires either strong selective pressure or intentional design. Part 9. The solar flow and the story of shadows. The Hubble telescope captured images of a three-eyed atlas in mid-September 2025, sparking months of speculation and analysis. The morphology immediately caught the eye of everyone familiar with typical comet shapes. Dust and gas were primarily drawn towards the sun, creating what astronomers call an anti-tail, a structure directed forward, opposite to the classic anti-solar tail that defines the iconic silhouette of a comet. The solar continuation in Hubble images was measured to be about 10 times longer than its width, indicating either a highly collimated flow directed straight at the sun or a wide trail of dust viewed almost edge-on from Earth's position. Geometry matters for the interpretation of what we see. At the moment of Hubble's observations, the sun, Earth, and a three-eyed atlas formed a configuration where the Earth was just 10 degrees from the line connecting the sun and the comet. This means we observe the object almost directly along the axis pointing to the sun, seeing any solar structure in its most elongated projection. If the object had a symmetric coma, we would expect to see a roughly round or elliptical shell, possibly with a slight elongation due to the formation of a dust tail. Instead, Hubble captured a pronounced needle pointing at the sun, with a much weaker and shorter anti-solar tail behind it. Loeb and his colleague Eugene Quito modeled this geometry in their analysis, noting that the true three-dimensional dimensions of the solar structure are likely even larger than the 10-to-1 ratio suggests, as we see it slightly shortened even when 10 degrees off the axis. Anti-tails are not unusual for comets in the solar system. They occur when we view the orbital trail of the comet's dust from the side, so particles ejected earlier in the comet's orbit appear to project in front of the nucleus from our line of sight, although they are physically behind along the orbital path. Classic examples include comets, such as Comet Roland, observed in 1957, which displayed a notable tail appearing directed towards the sun, explained only by the geometry of observing its dust trail. Unlike the three-eyed atlas, the antipode of the tail with its extreme aspect ratio and brightness relative to the anti-solar tail suggests something more than just a geometric projection. В исследовании, проведенном с помощью телескопа Хаббл, было предложено, что анизотропное излучение происходит с горячей стороны ядра кометы, где пыль и газ выделяются преимущественно из областей, прямо освещенных Солнцем. This creates a real physical concentration of material on the side facing the sun, rather than just a visible concentration due to the angle of view. Anisotropic gas emission is often observed in comets, as their nuclei are not homogeneous spheres with symmetrical activity. Active areas, areas with open drifting ice, or regions with various thermal properties can concentrate jets in specific directions. The rotation of the core carries these active zones through cycles of day and night, altering the gas emission pattern. However, most comets exhibit multiple jets at various angles rather than a single dominant concentration towards the sun. The physics of the three-eyed atlas will apparently prefer to direct gas straight to the sun, and to maintain this pattern over several weeks of observation, either a very specific shape and state of the core's rotation, or a surface composition where the areas facing the sun have fundamentally different volatile content compared to other regions, is required. Both options are possible within natural processes, but both contradict the central tendency of comet behavior. Speculative mechanical analogies begin to emerge here, which must be clearly defined as we enter the realm where physics and imagination blend. If the three-eyed atlas had a reflective surface instead of an absorbing dusty one, the sunlight hitting the daytime side would reflect back to the sun instead of being absorbed and re-emitted as heat. This mirror reflection could create a concentrated increase in brightness towards the sun, appearing in images as a bright beam, even if no material is actually emitted. This can be imagined as a solar sail, where flat reflective panels disperse sunlight primarily in directions determined by the surface orientation. However, the analogy quickly loses meaning, as solar sails are designed to be flat and highly reflective, while natural bodies are usually rough and dark. Nevertheless, this principle illustrates how surface properties can create directed optical effects that can be masked as streams in images. Another speculative analogy suggests that streams of radiation pressure resemble the exhaust of an ion engine. Ion engines used on spacecraft for highly efficient propulsion work by accelerating charged particles and ejecting them at high speed. The exhaust stream of the ion engine is highly collimated, creating a narrow stream of material trailing behind the spacecraft. If a three-eyed atlas somehow created a stream of charged particles or ionized gas directed at the sun, it might appear as a bright solar extension in optical images due to the electric charge from solar wind or some active emission mechanism. The physics necessary for this scenario is entirely speculative, and there is no natural mechanism that could create a stable solar ion flow from a comet. However, if we consider artificial hypotheses, directed emission of some kind becomes at least conceptually possible. The third speculative idea considers directed gas emission intended for thermal regulation. Engineering spacecraft manage heat using radiators, surfaces specifically oriented to emit thermal energy into cold space. If the three-eyed atlas were a design created for survival near the sun, it could use gas emission or sublimation of surface materials as an active cooling mechanism, with emission primarily directed towards the sun to enhance cooling efficiency. It would be like a shield against heat, where the material evaporating from the sunlit side carries away thermal energy and prevents overheating of the interior. Chemistry plays a huge role here. The sublimation of carbon dioxide, confirmed by the James Webb Telescope as the dominant volatile component, is an excellent cooling agent due to its high latent heat of sublimation. The use of carbon dioxide as an engineering fluid for thermal regulation is not absurd from a physics standpoint, although claiming that a three-eyed atlas utilizes engineering thermal management would be quite bold without sufficient evidence. There are natural explanations for the anti-tale that have been published. A recent preliminary publication, appearing on the R-CHIP platform at the end of September 2025, modeled the solar morphology of a three-eyed atlas using an isotropic survival radius of sublimating icebergs. The main idea is that the dust grains ejected from the core contain frozen water, which continues to sublimate as the grains move through the comet. Grains heading towards the sun experience stronger solar heating and sublimate faster, creating a population of grains that survive longer in anti-solar directions than in solar ones. This differential survivability can lead to a visible concentration of smaller grains or gas towards the sun, while larger grains, resistant to sublimation, form a classic anti-solar dust tail. The model reproduces the observed morphology of a three-eyed atlas without resorting to artificial structures or exotic physics. This natural explanation expands our understanding of cometary dust dynamics rather than questioning the fundamental assumption that we are dealing with a comet. The question is which explanation is more economical: natural and isotropic processes that are complex but plausible within established physics, or artificial structures that are conceptually simple but require abandoning the assumption that interstellar objects are natural bodies. Occam's razor, a principle stating that simpler explanations are preferable, does not unequivocally favor one side, as simplicity depends on one's assumptions. If you assume that interstellar objects are always of natural origin, then even complex natural models are simpler than the assumption of artificial objects, as they do not require the unusual claim that artificial objects travel through interstellar space. If you do not have a predetermined position regarding the origin of interstellar objects, a simple engineering explanation may be more economical than imposing a multitude of exotic natural processes. Loeb proceeds from an agnostic premise. Fundamental astronomy operates on a natural premise. None of the positions are inherently wrong, but they lead to very different interpretations of ambiguous data. What new observations could distinguish engineering interpretations from natural ones regarding morphology directed towards the sun? Variability patterns may serve as one of the diagnostic tools. If the solar flow is linked to the rotation of the core, We should observe periodic modulation as active areas enter and exit sunlight. Natural flows typically exhibit rotational modulation with periods ranging from hours to days, depending on the core size and its rotation speed. If the solar feature of the 3-in-1 atlas remains stable in brightness and morphology over timescales exceeding reasonable rotation periods, it will be unusual and potentially indicate a non-rotational mechanism. High-resolution images that distinguish the core and nearby flows will show whether activity is occurring from distinct active regions or from a more homogeneous outburst on the solar side. Polarization maps can distinguish scattered sunlight from dust and mirror reflections from smooth surfaces. Spectroscopic monitoring of solar features compared to the anti-solar tail can reveal differences in composition, confirming whether we see different particle populations or various physical mechanisms. None of these observations were completed with sufficient resolution and frequency to definitively resolve the issue. The Hubble Space Telescope provided morphology but did not ensure high temporal resolution of variability. The James Webb Telescope provided data on composition but did not allow imaging of the core. Ground-based spectroscopy revealed emissions of metals but did not provide spatially resolved maps of where these emissions originate. The Mars walk could have offered closer observation points from orbital devices that could provide important data. But as we discussed in the first act, this data was either not collected, not published, or not processed with enough priority to appear in public archives. The stream directed towards the sun remains an open question. Beautiful in images and impressive in its geometry, it nevertheless remains uncertain in its origin. This uncertainty underlies why the 3-in-1 atlas attracted public attention in a way that the 2-in-1 Borisov never did. Borisov was peculiar in composition, showing chemical signatures different from the comets of the solar system, yet its morphology was quite ordinary. He resembled a comet and acted like a comet. 3 Atlas looked like something trying to be a comet, but not quite succeeding at it. A stream of sunlight, a blue spot from Mars, nickel without iron, an almost elliptical trajectory. All these elements create a general feeling of something unnatural, even if it's hard to articulate why. And in this irregularity, in the gap between what we expect and what we observe, a space opens for speculations that would be immediately dismissed if the observations were more mundane. We have already studied the object itself, its orbit, chemistry, and morphology. We identified 7 anomalies and considered how each could be natural, artificial, or some combination we haven't yet thought of. But there is one more element in this story that we have not discussed properly, and it is the element that transforms scientific curiosity into something darker and conspiratorial. Silence. A gap between what observers expected and what agencies provided. The perception, whether true or not, that information is being hidden, distorted, or delayed for reasons beyond ordinary scientific caution. This perception, and the fertile ground it creates for speculations about concealments and hidden truths, will become our next challenge. Because if the 3 eyes and atlas are indeed unusual, the question is not only what it is. The question is, who controls the history of its discovery, and what happens when that control weakens? Part 10. Hiding in plain sight. Avilov set expectations in his essays before the flight with clear specifics. A high-resolution camera on a Martian reconnaissance orbiter could provide diameter limits of about 30 kilometers per pixel. The Mars Express and ExoMars Trace Gas Orbiter could contribute to infrared spectroscopy. The Perseverance Mars CAM-Z and other instruments could record observations of the night sky if mission planners allocated time. The observation window spanned from October 1st to 7th, with the closest approach on October 3rd. A multitude of independent platforms with various observation geometries and diverse spectroscopic capabilities were directed at an object that had been monitored and predicted for months. The community awaited a stream of data. Instead, only a drop came, followed by a leak that bypassed official channels. Publications from NASA's Mars missions remained silent right after the closest approach. Regular daily or almost daily updates of raw images from Perseverance continued, but they only showed rocks, wheel tracks, and Martian landscapes. There were no obvious shots of the night sky with a dim interstellar visitor. There were no press releases about discoveries or lack thereof. There were no curated galleries of images with carefully crafted composites showing 3 and Atlas against the backdrop of a Martian sky. The high-tech archive, searchable by observation ID and target coordinates, showed no new records corresponding to the 3 atlases of the eye during the observation window. at least in the public catalog accessible to amateur researchers. The data coming from Mars remain technical and unlabeled, making it difficult to search for specific targets without prior knowledge of the observation planning. ExoMars TGO, the youngest of the Martian orbiters and still relatively new in scientific operations, focused its efforts on measuring gas traces in the atmosphere, without indicating that it was attempting to observe interstellar objects. This silence can be fully explained within the normal operation of the mission, and we must be fair in this, even when exploring why silence seems louder than neutrality. Data analysis takes time, especially for atypical observations that were not part of the original mission plan. Orbiters and rovers on Mars have priority tasks related to Martian science, geology, atmosphere, climate, astrobiology, and resource characterization for future humanitarian missions. Observing a temporary interstellar visitor is a bonus, an opportunity planned if the timing and direction of the spacecraft allow, but it is not prioritized over primary tasks. When data comes from such observations, it enters a processing queue for a higher priority dataset. Calibration requires matching the tool's direction with precise ephemerides for the target, which means waiting for updated orbital solutions from observers tracking Atlas III from Earth. Quality assurance requires checking for tool artifacts, cosmic ray hits, and processing errors before declaring the presence or absence of detection. This takes days or weeks, not hours. But the time gap between expectation and receipt creates fertile ground for alternative narratives. The government crisis in the USA, which began on September the 30th and affected some NASA operations, became a convenient explanation, although crises do not halt deep space missions or data collection. Public relations offices reduce their activities during crises, press releases are delayed, non-essential employees are sent on forced leave, which can slow the labor-intensive process of curating data for public release. But spacecraft continue to operate. Telemetry continues to arrive at ground stations. The critical analysis of the mission continues. The crisis has affected communication more than capabilities, but in a story already ripe for conspiracy theories, delays in communication appear as deliberate suppression, regardless of their real cause. The circular loop that amplified the leak about the mass camera Zed from Schmaus also intensified narratives about the agency's silence. Discussions in Blusky and X threads were filled with speculations about why official data had not emerged. Reddit communities debated whether Martian orbiters had been monitoring a target or if the observation plans had been quietly canceled. Content creators on YouTube posted videos questioning whether NASA is hiding evidence of an interstellar probe, using a sincere lack of public data as an argument for conspiracy theories. Publications in similar outlets carefully balanced between highlighting public speculation and supporting it, providing a platform for questions without the obligation to answer. Each new round of discussions increased the distance from the technical reality of standard data processing times, creating a social reality where silence equated to abuse. Historical analogies simultaneously softened and fueled suspicions. The discovery of Oumuamua in October 2017 was met with months of uncertainty regarding its nature, composition, and origin. Initial observations showed an elongated light curve, corresponding to a rotating, highly elongated object. Subsequent astronomical measurements revealed a non-gravitational acceleration that could not be explained by ordinary cometary outgassing, as no coma was detected. Loeb's hypothesis that Oumuamua might be an artificial light sail emerged in 2018, sparking lively debates that continue to this day. During this period, data publications were slow, analyses were contested, and the gap between initial discovery and scientific consensus allowed speculation to thrive. Uncertainty was real, but it arose from the limitations of observations and genuine scientific uncertainty, not from institutional suppression. The detection of an interstellar meteor by U.S. government sensors, declassified and analyzed by Loeb's team, led to an expedition to the ocean floor that reported finding metallic spirals of possible interstellar origin. These statements faced immediate criticism from researchers who claimed that the spirals were terrestrial pollution or misidentified cosmic spirals from ordinary meteoroids. The laboratory analyses did not align in their assessments of isotopic ratios and elemental compositions. Loeb insisted that his team's conclusions support an artificial, or at least anomalous, origin. Critics claimed that the data aligns with natural explanations and that extraordinary claims are based on ordinary measurements. The dispute remains unresolved, but it established a pattern in which Loeb's public essays preceded formal reviews. while institutional scholars opposed interpretations they deemed speculative and acted as public observers. A scientific debate was happening in real time through publications on platforms and preliminary reports, rather than waiting for journal publications. The Project 3 and Atlas fit perfectly into this scheme. Leo's essays accumulate anomalies and pose questions before agencies make official statements, while active observations like the leak about Mars stack verification trigger viral dissemination. Institutional silence caused by caution, delays in processing, or the logistics of closure is interpreted as evidence rather than absence. Public perception outpaces scientific data, creating expectations that agencies cannot meet as their timelines are measured in weeks, while social media operates in hours. Is there a scenario in which agencies would actually hide data indicating something unusual? The question has a conspiratorial nature, but it should be taken seriously as the answer shapes our understanding of silence. If initial images from spacecraft like Vysotka or Mars Express show morphology clearly inconsistent with a natural comet, such as sharp edges or regular geometric patterns, or reflections indicating machine surfaces, will agencies release this data immediately to the public, or will they first conduct internal checks, consult experts, verify possible instrument artifacts, and possibly coordinate with other agencies before making any statement? The cautious response is that unusual data will undergo thorough verification before publication, not out of a desire to hide information, but due to the enormous consequences of errors in any direction. Premature announcement of the artificial origin of something that turns out to be a natural comet with unusual properties undermines trust and fuels conspiracy theories. Premature rejection of anomalous signs as artifacts when they are real hinders scientific understanding and potentially conceals information of deep importance. The most likely outcome is a dull scenario. Martian probes indeed observed Tri-and-I Atlas during the flyby window. Some observations were successful, while others failed due to targeting errors or unfavorable lighting conditions. Successful observations are processed through the usual channels of analysts who work on multiple projects under limited budget and time constraints. Preliminary results are checked for model conformity compared with Earth observations and prepared for publication through peer-reviewed channels. This process takes weeks or months, not days. When the results appear, they will likely show that 3-and-I Atlas corresponds to an exotic, yet natural comet, expanding our understanding of the diversity of interstellar objects without the need for artificial hypotheses. The data leak from Mastcam Z will be explained as a processing artifact, incorrect registration, or, at best, a marginal detection of diffuse coma, adding no significant new information compared to what has already been provided by James Webb and Hubble. But a dull script satisfies no one emotionally involved in this mystery. It does not explain why Schmooze showed blue when all other data was green or neutral. It does not take into account the total of 7 anomalies cataloged by Lob. This does not resolve the inner disharmony that many observers feel when looking at the composite data of 13 eyes and does not take into account the distant, but not negligible possibility that we are actually dealing with something artificial. Silence can be a sincere warning before an opening that can shatter existing paradigms. And the leak of an image is not an artifact, but a glimpse of truth breaking through the cracks of institutional control. We are at a crossroads of narrative. The second act described the object and its peculiarities, orbital precision, chemical anomaly, morphological features, as well as the informational dynamics surrounding it. The third act must confront the consequences. If 13 eyes are just an exotic comet, what does that tell us about interstellar space and the formation of planetary systems? If this is something greater, something created, or deliberately delivered, what does it mean for our understanding of the mind in the universe and our place in the cosmic ecosystem? And how can we, as individuals without access to secret data or internal information, bridge the gap between what we are told and what we suspect? These questions will be our next topic, as reflections on the real or an artifact from Mars have already changed the course of the discussion. They made the unimaginable tangible. And once this threshold is crossed, returning to the previous state becomes impossible. Part 11. Mars, the Silent Witness. If the leak is indeed genuine, if the Perseverance rover truly captured 13 eyes during its passage through the Martian night, then Mars itself becomes the most important witness to this event. not because it is astronomically unique, but because Mars offers verification paths that cannot compete with observations from Earth. Distance matters, geometry is important, and control over the narrative becomes critically important when it comes to statements that challenge fundamental assumptions about what moves between the stars. There are secondary ways to confirm, which are easy to list, even if accessing them is difficult. Mars orbiters, especially the Mars Reconnaissance Orbiter with its high-resolution camera, observed the 13-eyed creature from much closer positions during the flyby on October 3rd than any telescopes on Earth. 29 million kilometers separate Mars from the 13 eyes at the nearest approach. 150 million kilometers separate Earth from Mars at this moment of both planets' orbits. Let's add changing geometry as the 13-eyed entity moves through the inner solar system, with observations from Mars potentially providing spatial resolution and brightness sensitivity that Earth cannot offer. If the high-resolution image successfully captured the target, the data should show either a point source, an extended comet, or nothing, depending on the true nature and brightness of the object. A point source would indicate a compact structure. An extended coma will confirm the hypothesis of a natural comet. Nothing indicated that the object was less bright than expected, or that guiding arrows hindered its detection. Spectroscopic data from Mars orbiters complements information about its composition. Mars Express is equipped with a modest visible and infrared mineralogical spectrometer that could theoretically capture 3 spectra from the three-eyed atlas, if the observation was properly planned and executed. The ExoMars instruments designed for atmospheric analysis are less suitable for targeted observations or spectroscopy, but they could attempt measurements during the flyby. These observations would complement the data on composition obtained from the James Webb Telescope, potentially revealing differences in the chemistry of the coma, considering the closer position of Mars. If the ratio of carbon dioxide to water changed depending on the angle of view, or if the emission lines of metals showed different relative intensities from Mars and Earth, it could clarify the models of the coma structure and ejection mechanisms. The Mars rover Perseverance could attempt to repeat observations after the first data leak. The rover operates autonomously between command uploads, but mission planners can schedule sequences days in advance. If the primary stack from October 4th indeed recorded the three-eyed atlas, the planners could have ordered additional night shoots in the following nights to track the object's movement and confirm its detection. The fact that no subsequent stacks were disclosed may indicate that either further observations were not planned, or they were planned but failed, or they were successful, but the information is being withheld for a coordinated release. Each of these possibilities has its consequences. The absence of subsequent observations may mean that the mission planners did not trust the initial detection, or that the rover's resources were directed to other tasks. The failure of subsequent observations indicates that the detection limits were extremely sensitive to atmospheric conditions and targeting accuracy. Successful observations held for coordinated release may indicate that agencies view this as a significant discovery requiring careful presentation. The participation of various countries in the observations from October 1st to 7th was multifaceted and multi-layered, at least theoretically. NASA operates the Martian Reconnaissance Vehicle and Perseverance, while ESA is responsible for Mars Express and ExoMars TGO. Agreements on data sharing between space agencies mean that significant findings from one mission are usually communicated to others, allowing for coordinated observational campaigns and mutual verification. If NASA's devices discovered something unusual during the flyby of the three-eyed atlas, ESA would likely be notified and could provide its independent observations or analysis. The multinational nature of Martian research implies that a scenario of coordinated information suppression requires a conspiracy among agencies, cultures, and bureaucratic structures that are not prone to natural alignment. This does not make coordination impossible, but sets higher demands for maintaining operational silence among many independent organizations. The optics of closure and high stakes create the perfect environment in which we find ourselves. When the U.S. government shutdown coincided with Mars's flyby window, it provided a ready explanation for why NASA's public communication channels went silent, but the shutdowns did not affect the European Space Agency's operations. Mars Express and ExoMars TGO continued to operate normally. Their data continued to be collected and archived, and scientific teams in Europe faced no restrictions related to the closure. If European instruments had detected something unusual, there would be no reason to delay the announcement. The absence of any statement from ESA suggests that either European observations were unsuccessful, or they showed nothing unusual, or the delay is related to the same reasons that might explain NASA's silence. Multinational silence is harder to explain than simple logistical difficulties, leading to speculations that the reasons for the delay go beyond bureaucratic convenience. Geometry gives Mars a unique advantage that ground-based telescopes lack. The trajectory of the three-eyed Atlas crossed the front hemisphere of Mars during its flyby, indicating that Mars was in a favorable line of sight to observe the leading side of the object. The hemisphere was oriented towards the direction of movement through space. The geometry of observation from Earth positioned us more towards the side or rear of the hemisphere, depending on the specific date. This difference matters if the three-eyed Atlas has hemispherical asymmetries in brightness, composition, or structure. The reflective leading edge or concentrated gas plume towards the impact would appear brighter from Mars. Observers from Earth would see a different aspect, perhaps less bright, or showing various spectral characteristics. The lack of coordination between the brightness or color observed from Mars and Earth can itself be a diagnostic sign, revealing structures and asymmetries that would be invisible with only one perspective. What can be considered irrefutable evidence from Martian probes? The list is short but clear. Coordinated movement across several frames would confirm that the recorded event is a real astronomical object and not an instrument artifact, as artifacts do not move predictably across the sky. Spectroscopic lines matching the carbon dioxide-rich coma of JWST would confirm compositional consistency and support the hypothesis of a natural comet. Spectroscopic lines that do not match JWST, especially if they showed metallic emission or absorption features incompatible with comet chemistry, would require exotic explanations. Brightness profiles incompatible with an extended diffuse coma, especially if they showed compact sources or structured light distributions, would cast doubt on natural models. Chromatic consistency or inconsistency with the bluish spot, measured using multi-band photometry rather than processed RGB stacks, will help determine if the color anomaly is real or an artifact. By the beginning of October 2025, none of these irrefutable pieces of evidence had appeared in public data. This absence creates a silence that feeds speculation, leaving us in a state of uncertainty where data leaks exist as a social fact, discussed in various communities but not confirmed or refuted by additional data that could clarify the situation. Uncertainty can persist for weeks, or perhaps even months, until either the agencies publish the results of the flyby past Mars, or attention shifts to other disputes. However, for the attentive observers, those who followed the uncertainties of Oumuamua and his disputes, this scheme is familiar and evokes disappointment. Important questions remain unanswered, not because data is lacking, but because data flows and institutional caution create temporary gaps filled by speculation. Mars remains a silent witness. Its orbiting spacecraft and rovers may hold information that could resolve disputes or deepen mysteries. This information exists somewhere in telemetry streams and archival servers, waiting for human analysis and interpretation. Whether she will appear in days, weeks, or months depends on priorities unseen to us and decisions beyond our access. In this gap between event and revelation, we construct narratives that may or may not withstand future data. The information leak has already shaped these narratives, turning the 3 Atlas into an interesting interstellar comet into a Rorschach test, where believers see confirmation and skeptics see artifacts. Both sides use Mars's silence as evidence for their positions. We need to step back now and connect 3 Atlas points with a broader scheme that started with Oumuamua and continued through IM-1. Because if the 3 Atlas ships are merely the latest in a series of interstellar visitors that do not quite meet our expectations, then either our expectations are poorly calibrated, or we are witnessing the initial stage of a revelation that will change our understanding of our place in the cosmos. This scheme, and what it might mean, will be the next topics of our discussion. Part 12. From Oumuamua to Atlas, a scheme emerges. 3 data points do not create a trend, but they are enough to start questioning whether we see statistical noise or the first hints of a signal. The first object, Oumuamua, appeared in October 2017, becoming the first confirmed interstellar object detected in our solar system. Its discovery happened by chance when the Pan-STARRS telescope in Hawaii captured it as a faint point of light moving against the stars. Initial observations indicated an asteroid, a rocky body without the gas and dust coma that define comets. However, its trajectory and subsequent non-gravitational acceleration did not fully align with the asteroid hypothesis. The measured speed as a deviation from pure gravitational motion required either an asymmetric ejection, like a comet, or some other force acting on the object. Even with deep probing, no coma was found, which excluded the typical cometary ejection. Avi Loeb and his colleague Shmuel Bialy published a paper in 2018 proposing that the acceleration can be explained if Oumuamua is a solar sail, a thin reflective sheet moving under the influence of solar pressure. This hypothesis sparked much debate and was harshly criticized by most astronomers who deemed it unnecessary, as a slight emission of volatile substances that did not form a visible coma could explain the observed acceleration. Nevertheless, the article opened a door that subsequent observations never closed. The meteor IM-1, or interstellar meteor 1, entered this story through another path. The sensors of the U.S. government, designed to detect nuclear explosions, recorded a meteor entering Earth's atmosphere over the Pacific Ocean in January 2014. The analysis of the speed and trajectory of the meteor, conducted by Loeb's team using declassified data years later, suggested an interstellar origin based on its hyperbolic orbit. The material strength, determined by how the meteor disintegrated upon entering the atmosphere, indicated an unusual composition, potentially metallic, unlike typical stone or icy meteoroids. Loeb organized and led an expedition to the ocean floor at the impact site, extracting magnetic spirals from sediments that, according to him, displayed isotopic and elemental ratios incompatible with materials from the solar system. Independent laboratories disputed these claims, asserting that the spirals were either contamination from Earth, coal ash from shipping routes, or ordinary cosmic spirals from non-interstellar meteoroids. The contradiction remains unresolved. Loeb claims that his team's findings support the hypothesis of artificial or at least anomalous interstellar origin, while critics insist that the data has been misinterpreted. The three-eyed atlas represents a sharp increase in data volume compared to its predecessors. Oumuamua was discovered at the edge of the solar system, giving observers only a few weeks to gather data before the object became undetectable. Meteor M1 was the only event lasting seconds, leaving only signals of entry into the atmosphere and extracted debris as evidence. Three-eyed Atlas was discovered a few months before perihelion, allowing for extensive observational campaigns using flagship instruments. Spectroscopy with JWST provided the confidence in composition that Oumuamua lacked. The morphology obtained from Hubble revealed a structure that the single-point view of Oumuamua could not show, while ground-based spectroscopy detected metallic emissions that were not characteristic of previous objects. The flyby past Mars offered close approach opportunities that no previous objects had provided. Three-eyed Atlas is the most data-rich interstellar visitor we have studied, and yet, perhaps because of this richness, it is also the most ambiguous in interpretation. Observing Atlas's three eyes makes it stand out among typical comets of the solar system more brightly than its predecessors did among their comparative groups. Oumuamua's strangeness was mainly manifested in its dynamics, in non-gravitational acceleration without a visible coma. The strangeness in Odin was related to its composition, the presumed strength of the material, and the claimed isotopic anomalies. Atlas's three eyes combine dynamic, compositional, and morphological features into one object. Its trajectory, close to the ecliptic, with multiple encounters with planets, resembles the astonishing geometry of Oumuamua's approach. The claimed unusual metal ratios resonate with the disputed spherical chemistry of Odin. The formation of a coma dominated by carbon dioxide and directed towards the sun adds morphological and compositional elements that were not present in previous objects. Measurements of polarization, extending beyond known families of comets, add photometric anomalies and potential detection of mass on the surface, if indeed it exists, provides observational confirmation from a perspective that changes the entire history. Institutional reactions have also evolved in connection with three objects. The initial interest sparked by Oumuamua was met with resistance from mainstream science to the hypothesis of light sails, and most astronomers settled on exotic but natural explanations related to the outgassing of volatile substances like nitrogen or water ice. Oumuamua was met with skepticism from the very beginning, with many researchers questioning whether the meteor was truly interstellar and disputing the compositional characteristics of the recovered spirals. The three eyes of Atlas elicited a more complex reaction. Serious scientific articles describe it as an unusual but natural comet rich in carbon dioxide, while a parallel narrative structure considers it a potentially artificial object, or at least deserving of serious consideration of this hypothesis. NASA and SA press releases emphasize the interpretation of the comet, highlighting compositional data obtained from the JWST telescope and explaining the morphology directed towards the Sun through natural degassing models. Media coverage is divided between outlets highlighting the main comet story and those amplifying the narrative about frontal anomalies. At the end of September, The Guardian published an article that directly opposed interpretations related to alien technologies, citing astronomers who claimed that the features of Atlas's three eyes were unusual but aligned with the natural diversity of comet populations. The article noted that carbon dioxide-rich comets exist in the solar system, that antipodes directed towards the Sun have natural explanations, and that attributing anomalous characteristics to artificial origins requires much more convincing evidence than currently exists. This institutional confidence, conveyed through authoritative journalistic channels, serves a function in the information ecosystem. She provides a counter-argument to speculation, basing public understanding on expert consensus, even when that consensus is less dramatic than alternative interpretations. The Galileo Project, an initiative focused on systematically searching for technological traces of extraterrestrial civilizations, is based on the principle of an open but not empty mind. The project's motto emphasizes that unusual claims require evidence, but rejecting artificial hypotheses in advance without investigating the facts is unscientific. This approach positions Loeb and his colleagues as methodological skeptics rather than believers willing to follow the data wherever it leads, instead of fitting interpretations to convenient assumptions. Critics argue that this position is asymmetric, and that Loeb emphasizes artificial hypotheses while neglecting natural alternatives, creating an impression of evidence for artificiality that does not actually exist. Debates are held not only about scientific methodology and communication, but also about specific observations. The pattern emerging from observations of Oumuamua, IM1, and 3I Atlas manifests in increasing uncertainty and complexity. Each subsequent interstellar visitor provided more data, more opportunities for detailed analysis, and more features that challenge simple categorization. If this trend continues, future interstellar objects will be detected earlier, their observations will be more complete, and the data obtained will be even richer, which will either resolve uncertainties or deepen them. It remains to be seen whether this path will lead to a consensus that interstellar objects are naturally diverse in unexpected forms, or to the accumulation of evidence that some interstellar visitors are artificial. But 3I Atlas, with its combination of reliable observations and constant anomalies, represents the sharpest test of how we can navigate the space between natural and artificial interpretations. We need to clearly outline the scenarios. What competing explanations exist for the 3I Atlas, and what is needed to choose between them? This is a theoretical work of the next section, followed by an exploration of why this particular case seems qualitatively different from previous disputes, and what this difference tells us about our readiness to confront opportunities we have historically rejected. Part 13. Theoretical Scenarios. Three competing models attempt to encompass everything we have observed regarding the 3I Atlas, each with implications that extend far beyond a single astronomical object. Let's consider them with due attention, as the choice between these scenarios is not just an academic exercise, it is a statement about what we consider possible in the universe and how we interpret ambiguous evidence. Scenario A presents the 3I Atlas as a natural megacomet, exotic yet fundamentally ordinary, formed by processes we understand even if we have not observed their exact results before. The composition, rich in carbon dioxide, securely established using JWST's near-infrared spectroscopy, fits perfectly into this model. The James Webb Space Telescope discovered a ratio of carbon dioxide to water of about 8:1, which is significantly higher than typical comets in the solar system. This can be explained by the fact that the comet 3I Atlas formed beyond the freezing line of carbon dioxide in its parent planetary system. The freezing line of carbon dioxide is farther from the star than the freezing line of water, as carbon dioxide requires lower temperatures to freeze. Objects forming in this cold outer region accumulate rich carbon dioxide ice, while water may have been lost due to early heating or simply absent at such an orbital distance. The Spherex mapping, covering an extended carbon dioxide comet at distances exceeding 348,000 kilometers, confirms active and sustained gas emissions consistent with a large core, rich in volatiles, reacting to solar heating as it approaches perihelion. The anti-tail, directed towards the Sun, and modeled using Hubble telescope analysis as an anisotropic ejection from the hot side, naturally fits into this scheme. Comets with irregular shapes and uneven surface compositions regularly display jets and morphological asymmetries. The extreme aspect ratio of the solar sign 3 and Atlas contradicts typical expectations, yet does not violate them. Recent models of anti-tail formation based on differential sublimation rates of ice particles provide a physical mechanism that reproduces the observed morphology without the need for exotic processes. Particles heading towards the Sun sublimate faster, creating an apparent accumulation of material in that direction, even if the actual emission pattern may be more symmetrical. This is subtle physics, but it fits perfectly within the natural behavior of comets. Measurements of polarization, though unusual, placing 3I Atlas beyond the known families of comets in parameter space, are still compatible with natural populations of dust particles if one allows for unusual distributions in size, shapes, or compositions. Polarization is sensitive to the properties of particles, and in our sample, there are only a few dozen well-characterized comets. The parameter space of natural dust is certainly larger than we have explored. 3 and Atlas may simply be demonstrating a population of dust we have yet to encounter, expanding our understanding of what cometary particles might look like rather than indicating artificial origins. Metallic emissions, atoms of nickel and iron found in the coma, despite their mysterious ratios and thermal requirements, are now known to occur in other comets as well. Mechanisms remain a subject of discussion, but organometallic compounds and radiation-heated particles containing metal provide plausible natural pathways. Scenario A is strong in its conservatism and reliance on established physics. He does not require new fundamental processes, a rejection of the assumption that interstellar guests are natural bodies, or a reference to intelligence or engineering. His weaknesses are also obvious. He requires the combination of several unusual characteristics, each of which lies on the edge of natural distributions, in one object. High carbon dioxide levels, extreme antitail morphology, unusual metal ratios, and abnormal polarization near the ecliptic trajectory. All these factors can be explained separately, but together, they seem unlikely. How many improbable characteristics can be combined before the expansion of natural diversity becomes a less economical explanation than considering alternatives? This is a question of judgment, not computation, and different scientists with various biases will draw the line in different places. Scenario B suggests the existence of a fragmented interstellar research station, a purely speculative idea, but worth considering from a technical perspective. In this model, the depletion of nickel compounds is viewed as a sign of artificially created materials, clearly manifesting under solar heating, with the ratio of nickel to iron reflecting intentional alloy choices rather than cosmic abundances. Industrial stainless steels and superalloys use concentrations of nickel that significantly exceed natural ratios, as nickel enhances corrosion resistance, strength at high temperatures, and other desirable properties. If the triatlas object is a probe or its fragment made from such materials and currently experiencing thermal stress at perihelion, then the ablative surface will release metallic atoms in specified ratios into space. Spectroscopy would record these atoms as anomalous emissions, exactly what the forehead asserts while observing in the triatlas spectra. The solar antitail in this model becomes an artifact of thermal control or a sign of radiation pressure. If the object has a reflective outer shell optimized to minimize thermal absorption, sunlight reflecting off this surface will create a brightness increase in the direction facing the Sun, which may appear as a gas jet emission in images. As an alternative, if the object actively manages heat through directed ablation, preferring to shed material towards the Sun for maximum cooling efficiency, this will create a real radiation pattern matching observations. A cloud rich in carbon dioxide could serve as an artificial cooler, specifically used for its high sublimation enthalpy and inert chemistry. It could be a disguise. A layer of volatile ice is applied to make the object look like a comet from afar, hiding its structured internal mechanism. The nearest ecliptic trajectory with multiple planetary encounters becomes a defining feature in Scenario B, rather than a random detail. A probe designed to explore our solar system would naturally choose a trajectory aligned with the plane of the planets, maximizing scientific results by allowing close approaches to several worlds in one pass. The timing that ensures meetings with Venus, Earth, Mars, and Jupiter over 6 months reflects thoughtful mission design rather than lucky geometry. The size of an object potentially reaching 5 kilometers or more based on brightness and acceleration constraints makes sense for an interstellar mission where protection, fuel, tools, and redundancy require mass and volume. Smaller probes may be more fuel efficient, but larger devices are better protected from damage caused by micrometeoroids and radiation during interstellar flights, which can last from thousands to millions of years. Compelling evidence for scenario B includes structured light curves that do not align with random rotation, as well as recurring patterns suggesting controlled orientation rather than chaotic spinning. High-quality images that allow distinguishing geometric features, edges, panels, or regular structures will be crucial. Spectroscopic detection of mission or absorption lines that have no natural explanation, synthetic molecules or isotopic ratios that cannot be obtained through stellar nucleosynthesis or natural chemistry would seriously consider the possibility of artificial origin. Radio emissions or modulated optical signals would be clear evidence. So far, none of this has been discovered, which does not disprove the hypothesis, but means it is based on the interpretation of ambiguous data rather than clear positive evidence. Scenario S explores the possibility of disguising an artificial comet. This is the most speculative option, where a three-eyed atlas is essentially artificial but deliberately created to mimic a natural appearance from a distance. Reflective coatings or smooth surfaces can be wrapped in cloaks of volatile substances, carbon dioxide and water, which sublimate under solar heating and create the appearance of cometary activity. A blue spot from Mars in this context represents a view of a hidden reflective structure, where the icy mantle is thin or absent, showing a neutral or shifted blue reflection that differs from the reddish light scattered by dust, predominant from other angles. Carbon dioxide serves a dual function: thermoregulation through evaporative cooling and masking observations, creating spectroscopic signatures that observers interpret as cometry. This scenario is more complex to test as it is designed to create ambiguity. Successful camouflage, by definition, mimics a natural appearance well enough to avoid triggering artificial hypotheses unless one looks very closely at the settling sequences. The plausibility issues are significant. Why would an interstellar probe resort to camouflage? If the civilization that sent the signal wanted to remain hidden, it would have been easier not to enter our solar system. If they wanted to be discovered, then overt signals would be more effective than subtle anomalies that provoke debate rather than consensus. The strategy of camouflage makes sense only if the goal is selective disclosure of information. To be noticeable enough to attract the attention of advanced observers, while remaining ambiguous enough to maintain plausible deniability or avoid panic among less developed civilizations. This approach to understanding alien intentions is essentially speculative, but within this logical realm exists Scenario C. The ability to verify predictions allows us to track observations that could distinguish scenarios. Уточненные соотношения никеля к железу, полученные с помощью высокосигнальной спектроскопии на различных гелиоцентрических расстояниях и углах фазы, могут проверить, сохраняется ли поведение металлов постоянным, что поддерживало бы гипотезу о создании искусственного состава, или же оно изменяется, что указывало бы на естественное гетерогенное выведение газов. The change in polarization dimensions as a three-eyed object moves away from perihelion will show whether the properties of the dust change with distance in accordance with the natural sublimation process or remain anomalously constant. Subsequent images from HiRISE or JWST can clarify the size and morphology of the core, allowing the distinction between compact reflective objects and diffuse extended comets. Research on Mars with transparent methodology and independent verification will help determine whether the blue lubricant is real or an artifact. Lioba's rhetorical journey in his essay shifted from depicting an object with three eyes as anomalous to increasingly using language that implies artificial origins without making explicit statements. This is a cautious approach that maintains scientific credibility by avoiding definitive statements while preparing the audience to contemplate possibilities they might otherwise dismiss. This strategy worked, as the three-eyed object attracted much more public attention than the two-eyed object, despite both being interstellar comets. Whether this serves science or creates sensationalism around uncertainty depends on your perspective. Critics argue that it clouds clear thinking, elevating speculation to the level of established scientific data. while supporters believe it helps maintain openness to possibilities that institutional science may prematurely dismiss. These scenarios raise a fundamental question about evidence and interpretation. How much uncertainty are we willing to tolerate before considering exotic explanations? How many anomalies must accumulate before natural diversity becomes a less economical explanation than artificial design? There is no answer here, as the question depends on prior assumptions about the ratio of artificial and natural objects in interstellar space. If you believe that technological civilizations are widespread and some are engaged in interstellar exploration, then artificial explanations for anomalous objects deserve serious consideration as soon as natural explanations require many coincidences. If you think that technological civilizations are rare or that interstellar travel is extremely difficult, then natural explanations remain preferable, even if they require combining unlikely characteristics, since artificial alternatives are by default even less likely. An object with three eyes does not alleviate this tension. Rather, it intensifies it, prompting a discussion about the readiness of institutions to handle discoveries that challenge the foundations of our assumptions about cosmic solitude. Part 14. The blur that changes everything. Time, half a second. We return to the image, a barely noticeable blue spot against the backdrop of a Martian night composed of numerous frames from mass cameras. It was widely available, discussed on social media, and never received official confirmation or denial from the agencies controlling access to raw data that could clarify its status. Is this an artifact of processing, a misinterpreted natural phenomenon, or a hint of something artificial? This spot has become a symbol of all the strange things associated with the three-eyed atlas, attracting the attention of those uninterested in spectroscopy or orbital mechanics. This uncertainty causes endless debates, as neither confirmation nor denial has come to dispel the questions. The information leak shattered the monopoly on narrative, demonstrating that in the era of public data, archives, and experienced citizen scientists, institutional control over information is permeable and dependent. There are parallel truths that must be perceived simultaneously. Reliable scientific data is real and impressive. The near-infrared spectrograph of the James Webb Space Telescope provided high-quality spectra, showing a predominance of carbon dioxide with a CO2 to H2O ratio of 8 plus or minus 1, a robust compositional finding that withstands any reasonable assessment of uncertainty. Sphere X displayed an extended carbon dioxide comet stretching for hundreds of thousands of kilometers, confirming active and sustained gas emissions corresponding to a large core rich in volatiles. The Hubble Space Telescope captured a morphology showing the extension of the anti-tail toward the Sun with a faint anti-solar tail, an unusual geometry linked to anisotropic radiation on the daylight side. Ground-based spectroscopy detected neutral emissions of nickel and iron, expanding the spectrum of metal-bearing comets and raising questions about the mechanisms of radiation. Polarimetric measurements placed Atlas's three eyes beyond the known parameters of comets, yet still within ranges that could be accounted for by extended dust models. These are real datasets obtained using flagship tools, processed by expert groups and documented in preprints and scientific articles. They represent a significant contribution to our understanding of the diversity of interstellar objects, regardless of how we ultimately interpret their meaning. The narrative of leakage also resonates as a social and informational phenomenon. The time of leakage, discrepancies in colors, silent cycles, optics of disconnections, multinational data control, all of this has created ideal conditions for speculation. This cannot be dismissed as pure conspiracy theory. Gaps are real, even if the explanations are mundane. The incomprehensibility is genuine, even if the natural interpretations are correct. Public interest in rapid information clashes with institutional channels designed for thorough verification, and in this clash, information leaks, and citizen science fill the vacuums left by official channels. Understanding this dynamics is as important as understanding the object itself, as it determines how future discoveries will be perceived and discussed. A decision that will help viewers follow this story responsibly can be clearly articulated, though its implementation may be complex. Specific data in the future may clearly tilt the scales in favor of natural or artificial interpretations, and we should pay attention to this data instead of allowing speculation to fill the resulting void. High-resolution core constraints from the James Webb Telescope or other instruments capable of distinguishing objects at small angular scales will help separate compact sources from more extended ones. The constant, unusual behavior of nickel and iron at various distances from the Sun and observed geometries will strengthen claims of compositional anomalies. Polar symmetry across a wider range of phase angles will test whether the properties of dust are truly anomalous or just unusual in comparison to the mapped parameter space. Repeated discoveries on Mars with transparent methodology and independent validation will help determine whether the blue spot is a real signal or an artifact of processing. Spectroscopic monitoring tracking the temporal evolution of emission lines will show whether the outburst is stable, periodic, or exhibits patterns incompatible with natural rotation and heating. None of these observations are guaranteed. The telescope's time is limited. Mars mission planners have priority tasks unrelated to short-term interstellar visitors. Budget constraints limit the possibilities for subsequent campaigns. The three-eyed atlas gradually quiets down, moving away from perihelion, making future observations increasingly difficult. The window for decisive measurements may close before we get answers, leaving the three-eyed atlas in a state of perpetual uncertainty, like Oumuamua, an intriguing example that neither confirms nor denies exotic hypotheses, but demonstrates how much we still do not understand interstellar space and what passes through it. This spot may not hide what is there. It may conceal what we are not yet ready for. It is a thought experiment that concludes our journey. Imagine for a moment that the three-eyed atlas is artificial, and that the anomaly in its foreheads is not a coincidence, but a signal indicating that the nickel ratio, morphology directed towards the Sun, and a trajectory close to the ecliptic suggest an engineered origin rather than an exotic nature. What will this mean for us as a civilization facing evidence that we are not alone in using technology in interstellar space? The consequences will cascade in practical and existential directions. Practical, because it will confirm efforts similar to the Galileo project and shift resource allocation towards systematic searches for technological signals. Existential, because it will end cosmic isolation as a working assumption and force us to rethink our place in what will suddenly become a much more populous and complex universe. But now let's assume the opposite. Suppose that the three-eyed atlas is exactly what modern science claims, an exotic yet natural comet from beyond our solar system, formed under conditions we do not observe locally, but are fully explainable within the framework of known physical laws. The consequences of this discovery will still be profound. We will learn that interstellar space produces a variety of objects that significantly exceed what we see in our solar system, that carbon dioxide-rich comets with unusual metallic emissions and abnormal polarization exist and periodically pass through our neighborhood, and that our theories of comet formation and evolution need to be expanded to account for this broader range of parameters. We will also learn something important about ourselves and our epistemology. We will understand that ambiguous data generates passionate debates, where biases and interpretative frameworks are as significant as measurements. Institutional science and public curiosity operate on different timelines and incentives, and maintaining adequate skepticism while remaining open to unexpected discoveries proves to be more challenging than it seems. Both outcomes teach us something valuable. Both contribute to the advancement of knowledge, though pointing in opposite directions. The worst outcome is constant uncertainty, when the three-eyed atlas disappears from sight before decisive observations clarify key questions, leaving us with a rich data set supporting multiple incompatible interpretations and providing no clear path for choosing between them. Exactly in this position is Oumuamua today, about which debates continue years after its departure from the inner solar system, as it is still proposed in both natural and artificial hypotheses supporting different positions. The three-eyed atlas risks facing the same fate if subsequent observations do not arrive quickly enough to change anything. The call to action is simple. Watch for important data releases. Monitor where high-risk restrictions appear on Mars, in the archives of orbital scouts. Check the data on the JWST or ES spectrum. Monitor subsequent observations published in preprints or press releases. Look for independent analyses of mass camera Z-frames if NASA makes them publicly available with sufficient metadata for reproducibility. Monitor whether the nickel-iron ratios remain stable or change as new spectroscopies are published. Track if the polarization measurements are refined with additional observations. These are the data that can change the situation, either eliminating uncertainty or deepening it even more, and, while observing the data, maintain adequate epistemic humility. We do not know what a three-eyed atlas is with complete certainty. We have measurements, models, and interpretations, but the quantity and accuracy of measurements are finite. Models contain assumptions, and interpretations reflect biases that vary among observers. The blue spot on Mars, real or artifact, has already changed the conversation, making the impossible conceivable. Millions of people realize that interstellar objects pass through our solar system, that we can observe them with increasingly sophisticated tools, and that what we discover may surprise us, challenging conventional beliefs. This shift in public consciousness matters, even if the three-eyed atlas ultimately turns out to be a natural comet. He prepares us for a future where the discovery of interstellar visitors becomes commonplace, where ambiguous cases like this will arise frequently, and where we will need frameworks to understand the evidence and conclusions that most of us have yet to develop. Perhaps this blur shows us exactly what exists: a faint detection of a coma of carbon dioxide seen from a unique perspective of Mars during a close approach. Tinted blue, due to the chosen processing that does not reflect physical reality. Perhaps it shows nothing, being an artifact of the overlay methodology or a feature of the tool that accidentally lands in the coordinates where we expect it to find something. Or perhaps it demonstrates what has been suggested all this time: a glimmer of reflected light from a surface that did not form through accretion in a protoplanetary disk, but was intentionally created in a manufacturing complex orbiting a distant star, launched to our solar system thousands or millions of years ago, and only now revealing clues about its true nature to those observers who are skilled or fortunate enough to notice the discrepancies. We do not know what this is. We cannot know, not now, perhaps never, unless subsequent observations confirm or clarify the uncertainty. But here is what we can know. The three-eyed atlas represents a test case for how we deal with discoveries that lie on the border between the natural and the artificial, between the familiar and the unsettling, between what we expected to find and what we might actually be observing. How we navigate this space as scientists, journalists, and active citizens will determine not only our understanding of this particular object, but also our readiness for what follows. Because whether the three-eyed atlas is the third natural interstellar comet or the first confirmed artificial interstellar probe, it will not be the last strange object we discover in our cosmic neighborhood. The sky is vast, the galaxy is old, and we have only just begun to carefully observe what moves among the stars. The next Oumuamua, or three-eyed atlas, may be discovered tomorrow, next year, or in a decade. When he appears, we will be better prepared if we learn lessons from this case about how to balance skepticism with openness, caution with curiosity, and institutional expertise with distributed verification. This blur, whatever it may be, has given us this opportunity. How we use it depends on us.